Somewhere, quietly glowing in the vast ocean of the Milky Way, hidden within the constellation Centaurus, there is a star that has no right to exist. Astronomers catalogued it as HD 101065, but to those who've studied it, questioned it, and been haunted by it, it is known as Przybylski Star, a cosmic riddle wrapped in nuclear chaos. But before we continue, subscribe to the channel so you don't miss out on any of these videos. At first glance, HD 101065 seems like any other ordinary, mid-tier star, faint, relatively cool, and easily overlooked. It doesn't blaze with the glory of a red giant, nor collapse under the pressure of a dying neutron star. But its secret isn't in its brightness. It's in its fingerprint. When scientists turn their spectroscopes toward it, those magnificent instruments that decode starlight into elemental information, what they found wasn't just strange. It was, by all current scientific understanding, impossible. The star's atmosphere contained elements that shouldn't be there. Not just rare elements, but forbidden ones. Elements that don't exist in any stable form on Earth. Elements that are radioactive, short-lived, synthetic. The kind that decay in minutes, hours, days. Yet they were there, defying their own half-lives, glowing in spectral lines that had never been seen in a natural stellar environment before. In science, when a star defies theory, it's usually the theory that changes. But this time, the star itself was so absurd that even changing the theory didn't seem to help. What we were looking at wasn't just a chemically peculiar star. It was something far stranger. Something we couldn't categorize, couldn't explain, and most importantly, couldn't forget. A star that whispered, "You don't know everything." It's the kind of discovery that keeps you up at night. Because if one star in the galaxy can break the rules, how many others are out there? What else are we missing? And what if this isn't natural at all? In a universe bound by laws of physics, chemistry, entropy, Przybylski Star feels like an exception. A rogue data point. A glitch. Or perhaps a signal. Not in radio waves, but in elements. An alien periodic table written in plasma and gravity. It shouldn't exist. Yet it does. It shouldn't contain these elements. Yet it does. It shouldn't live long. Yet it persists. Przybylski Star is a quiet rebellion in the cosmic order. A protest against our assumptions. A spark of curiosity that refuses to be snuffed out. The story of this impossible star begins not with machines or equations, but with a man, a quiet observer beneath the Australian sky. Antoni Przybylski was not a name etched into textbooks or celebrated in academic fame when he made his discovery. In fact, in 1961, few outside of the astronomy community had even heard of him. But like so many who peer into the cosmos, he wasn't searching for fame. He was searching for truth. For patterns in the sky. For signals in the silence. Przybylski's life was shaped by upheaval long before he ever turned his eyes to the heavens. Born in 1913 in Poland, he grew up in the shadow of wars and shifting borders, under skies that changed flags but not stars. After surviving the turmoil of World War II, he emigrated to Australia, trading the familiarity of Europe for the vast, clear skies of the southern hemisphere. There, under the brilliant dome of stars that stretched across the Australian outback, he began his work at Mount Stromlo Observatory near Canberra. The equipment was modest by today's standards. But for a careful observer, even modest tools can uncover cosmic wonders. And Przybylski was nothing if not meticulous. He believed that starlight was a message, an unbroken line from a distant sun, waiting to be translated. One night, as he was analyzing the light from a relatively dim star catalogued as HD 101065, he noticed something off. The spectral lines, those fingerprints of stellar chemistry, didn't make sense. The usual markers, hydrogen, calcium, iron, they weren't behaving as expected. And stranger still, there were lines where there shouldn't have been any at all. Lines corresponding to rare earth elements. Lines that hinted at things no one had seen in a star before. At first, he must have assumed it was a mistake. A calibration error. A smudge on a plate. But the more he checked, the more consistent the anomaly became. This wasn't an error. This was real. He was seeing elements like strontium, europium, and lanthanum, heavy, exotic elements not typically found in abundance in stellar atmospheres. Some of them are difficult to even produce in Earth-bound laboratories. But they were there, shimmering in the spectrum of HD 101065, like graffiti on the walls of the universe. When he published his findings, they were met with fascination and confusion. Scientists were intrigued, certainly, but skeptical. How could such elements exist in a star? What process could put them there? For many, the data was too strange to accept at face value. But Przybylski stood by his measurements. And he wasn't wrong. As the decades passed and technology improved, later studies confirmed what he had found, and revealed even more. The list of strange elements in the star only grew. It turned out that Przybylski's star wasn't just odd, it was unprecedented. A one-of-a-kind cosmic anomaly that no model could explain. But Antoni Przybylski never sought to sensationalize his discovery. He remained a quiet, diligent scientist until his death in 1984. He never claimed aliens. Never sought media attention. He simply reported what he saw and let the evidence speak for itself. Today, HD 101065 bears his name. Not because he solved its mystery, but because he dared to notice it in the first place. In doing so, he became the first human to stumble upon what might be the strangest star in our galaxy. A star that defies time, defies decay, and perhaps defies nature itself. It's easy to imagine that something so strange, so alien, would be located in some far-flung corner of the universe, maybe billions of light-years away, hidden behind clouds of gas or cloaked by a black hole's event horizon. But the truth is far more unsettling. Przybylski's star isn't that far from us. In the vast scale of the cosmos, it's practically a neighbor. HD 101065 lies within the constellation Centaurus, a familiar figure in southern skies. Centaurus is a sprawling constellation, home to some of the most fascinating stellar objects ever discovered: Alpha Centauri, our nearest stellar system; Proxima Centauri, the closest star to the Sun; and deep within its structure, quietly pulsing without drawing much attention, is the anomaly, Przybylski Star. From Earth, it's about 355 light-years away. That means the light we see from it tonight began its journey toward us in the 1660s, long before humanity had even discovered electricity, let alone nuclear physics. The photons reaching our telescopes now began their journey when Isaac Newton was still alive. And what they carry, those spectral fingerprints, defies all that Newton, and everyone since, has taught us about the physical world. At magnitude 8.0, HD 101065 isn't visible to the naked eye. You won't see it while stargazing on a clear night unless you know exactly where to look and you're using a telescope. It doesn't demand attention. It hides in plain sight, a faint pinpoint in the vast darkness, surrounded by stars that obey the rules. But the space it occupies is not empty. Centaurus is a rich and ancient constellation, dating back to Babylonian star catalogs and later adopted by the Greeks as a centaur, a symbol of wisdom and wildness fused into one. Fitting, perhaps, that the strangest star known to science would reside there, a cosmic enigma buried in the body of a mythic creature. From our vantage point on Earth, looking toward Przybylski's star is like peering through a thin window into something deeper, more complex than we were ever meant to understand. It sits at a crossroads between what we know and what we can't yet comprehend. And even though it's only 355 light-years away, just next door, in galactic terms, its nature might place it further from us than any object we've ever studied. Because proximity doesn't always mean understanding. Just because it's near doesn't mean it's known. And just because it's small and dim in the night sky doesn't mean it's insignificant. Przybylski's star is a whisper from a nearby room, one that we can barely hear but can't stop listening to. Underneath the quiet flicker of HD 101065 lies a turbulent chemical drama unlike anything astronomers had ever seen before. At first glance, its light doesn't suggest anything alarming. It behaves like a relatively normal star in terms of its overall brightness and temperature. But when scientists examined its spectrum, the light revealed something far stranger, a cocktail of elements that, by all accounts, simply shouldn't be there. What makes this star so profoundly weird isn't just that it contains rare elements. It's the type of elements, the quantity, and the complete disregard for what should be possible in stellar physics. Most stars have atmospheres dominated by hydrogen and helium. These are the lightest, most abundant elements in the universe, forged during the Big Bang and continuously cycled through the lives and deaths of stars. In normal stars, heavier elements, what astronomers call metals, are present in trace amounts. Elements like calcium, magnesium, sodium, iron, and a few others might show up in the spectrum, giving scientists clues about a star's age, temperature, and composition. But Przybylski's star throws that entire rulebook into the fire. Its spectrum is filled with lines that correspond to rare earth elements, those heavy, exotic atoms that are difficult to form, and even harder to explain in natural abundance in a stellar atmosphere. We're talking about elements like lanthanum, neodymium, cerium, samarium, and europium. These aren't materials you expect to find just floating around in the outer layers of a star. In fact, the star's spectrum is dominated by these elements. They don't just appear in trace amounts, they take center stage. That's like walking into a bakery expecting the usual scent of flour and sugar, and instead being hit by the unmistakable odor of plutonium and promethium. And that's not even the weirdest part. Some of the elements observed in the star are radioactive, unstable by nature, with half-lives so short they shouldn't even exist in detectable quantities. One of the biggest red flags was the apparent presence of promethium, a rare earth element with no stable isotopes. That's right, not a single one. Every version of promethium decays quickly, some in mere minutes or days. Yet somehow, its spectral lines appear clearly in the atmosphere of HD 101065. This isn't just unusual, it's unthinkable. For promethium to be visible, it must be continuously produced, and it must be close to the surface where it can emit light before decaying. Otherwise, its short half-life would render it invisible long before its light ever reached our instruments. But promethium wasn't alone. Observations have suggested the possible presence of other elements like technetium, another synthetic, radioactive element with no stable isotopes, and perhaps even actinides, the family of heavy elements that includes thorium, uranium, and other atomic behemoths that typically reside at the end of the periodic table. Some astronomers have even speculated that transuranic elements, those beyond uranium, like plutonium or americium, may also be present in the spectrum. Let that sink in. This star, from over 350 light-years away, is displaying the signature of elements that are usually the product of high-energy physics experiments on Earth. The kind of stuff we see in particle accelerators, nuclear reactors, or the aftermath of thermonuclear explosions. What in the universe could produce that kind of chemical zoo naturally? Normally, stars do create heavy elements, but only up to a point. In stellar cores, nuclear fusion can convert hydrogen into helium, helium into carbon, carbon into oxygen, and so on up to iron. But fusing elements heavier than iron consumes more energy than it produces. So for those really heavy elements, like the ones seen in Przybylski Star, you need something more violent, a supernova, a neutron star merger, or some other high-energy, catastrophic event. Yet HD 101065 is not a supernova. It's not a white dwarf. It's not a remnant of some exotic explosion. It's still a main sequence or possibly a subgiant star, a relatively young calm star. That makes the presence of these elements even harder to explain. And the sheer variety of rare earth and radioactive elements present raises another baffling question: why this star? Among the hundreds of thousands of stars studied through spectroscopy, this is the only one, with this specific combination of elements. It's not like there's a whole family of stars like this out there. Przybylski Star stands completely alone. A chemical island adrift in a sea of conventional stellar behavior. What we see in its spectrum doesn't just break the mold, it shatters it. If HD 101065 had simply shown slightly higher levels of one or two heavy elements, astronomers might have explained it away with unusual stellar activity or magnetic diffusion. But when it shows a dozen or more rare earth and radioactive elements, most of them chemically synthetic on Earth, those explanations start to fall apart. And the distribution of these elements is strange, too. They don't appear to be evenly mixed, but rather stratified or concentrated in certain layers of the star's atmosphere. That implies some kind of sorting mechanism, possibly involving powerful magnetic fields or uncharted diffusion processes. But even those ideas only go so far. What's especially bizarre is that the star lacks the strong presence of hydrogen that most stars have. Hydrogen lines in its spectrum are unusually weak, almost as if the most fundamental element in the universe, the very fuel that powers stars, has taken a back seat to a parade of heavy atoms that shouldn't even be there. The picture this paints is almost surreal, a star with very little hydrogen, but rich in exotic, radioactive materials. It's like opening a can of soda and finding molten gold and uranium inside. All of this points to one inevitable conclusion: this is not just a star with a few odd quirks. It's an outlier in the extreme. A one-of-a-kind object that refuses to obey the most basic rules of stellar composition and evolution. It's a ghost in the machine of astrophysics. A cosmic anomaly that seems to exist simply to remind us how little we truly understand about the forces that shape our universe. And as we begin to uncover just how deeply unnatural its chemical signature appears, we're forced to ask uncomfortable questions. Could nature alone really produce such a chemical aberration? Or is there something more deliberate at play? Because when a star's ingredients include elements forged in human laboratories, you have to at least consider the unthinkable, that someone else may have forged them first, on a much grander scale. To truly grasp the strangeness of Przybylski Star, you have to understand how we even know what's inside a star in the first place. After all, we can't visit stars. We can't scoop up a sample of their plasma, bottle it, and study it under a microscope. They're far too distant, and even if we could get close, we'd be incinerated long before we reach the outermost layer. So how do we study them? The answer is light. Every star, including HD 101065, emits light across a wide range of wavelengths. From ultraviolet to infrared, from visible colors to radiation we can't see with our eyes, a star is constantly sending information outward at the speed of light. And hidden within that light is a kind of fingerprint, coded messages that reveal the star's composition, temperature, density, magnetic field, and motion. The tool we use to read this fingerprint is spectroscopy. Spectroscopy is, at its core, the science of splitting light into its component wavelengths, just like a prism splits white sunlight into a rainbow. But it's more precise than a simple rainbow. Scientists use special instruments called spectrographs to dissect starlight into a detailed spectrum, which shows not just color, but very specific lines, dark or bright bands, at particular wavelengths. These lines, known as absorption lines and emission lines, are caused by atoms and ions in the star's outer layers. When light passes through a cloud of gas, in this case, the star's atmosphere, certain atoms absorb very specific wavelengths of light. Each element has its own unique pattern of absorption lines, like a barcode. Hydrogen, helium, iron, calcium, sodium, all have very recognizable and precise signatures. By studying the positions and intensities of these lines, scientists can determine exactly what elements are present in the star and in what relative quantities. Imagine trying to understand the ingredients of a soup just by smelling it. Now imagine that you had a supersensory nose that could detect not just broad scents like onion or garlic, but individual molecules. That's what spectroscopy is, smelling the universe at a molecular level, but through the medium of light. So when astronomers studied Przybylski Star, they didn't go there. They didn't need to. They pointed their telescopes at it, gathered its light, fed it through a spectrograph, and stared at the result. And what they saw was nothing like the barcodes they had seen from other stars. Instead of the familiar patterns of hydrogen or helium, they saw a forest of lines, thin, closely spaced, high-contrast bars, that matched the fingerprints of extremely rare elements. Lines associated with lanthanides, actinides, and even radioactive elements that decay in mere hours. And just to be clear, these spectral lines aren't vague or interpretive. They are mathematically precise. Each electron transition in an atom corresponds to a specific energy level, which in turn corresponds to a specific wavelength. If a line appears at 410.2 nanometers, for instance, and that's the exact wavelength absorbed by a neodymium ion, then neodymium is almost certainly present in the star. That's how solid the science is behind it. It's like catching a criminal based on a perfect fingerprint match at the scene of the crime. There's very little room for ambiguity. And yet, the case of Przybylski Star wasn't just a strange match. It was a whole crime scene full of exotic fingerprints, some of which belong to suspects that aren't even supposed to be walking around freely in the natural world. Spectroscopy also allows scientists to study Doppler shifts, giving clues about how fast parts of the star are moving toward or away from us. It can reveal magnetic field strength through the Zeeman effect, where magnetic fields split spectral lines. It can even hint at stellar rotation and turbulence, by how broad or narrow the lines appear. But in Przybylski Star, the most jarring thing wasn't how the lines shifted or spread. It was what lines appeared in the first place. And it's worth noting, scientists didn't just look once and walk away. The star has been repeatedly observed over the decades, using progressively more sensitive equipment. Each time, the strange elements have remained. In fact, as our instruments have improved, more anomalies have appeared, more rare lines, more bizarre matches, more confusion. To put it simply, spectroscopy didn't just crack open the mystery of Przybylski Star, it made the mystery deeper. The better we got at reading the barcode, the more chaotic the information became. It's as if the universe handed us a library book in a language we thought we understood, only to discover it was written in symbols we'd never seen. And yet, the process itself is reliable. Spectroscopy is the bedrock of modern astrophysics. It's how we've mapped the composition of stars, galaxies, nebulae, and even exoplanet atmospheres. It works. It's not a guess or a glitch. So if the tools are sound, and the light is real, and the elements are clearly there, then the implications become much harder to dismiss. Because through spectroscopy, we're not just seeing the star, we're listening to it. And Przybylski's star is not singing the song of hydrogen and helium. It's playing a melody written in radioactive decay, synthetic atoms, and nuclear impossibilities. It's telling us something. We just don't know what yet. Promethium. Even the name evokes something forbidden, borrowed from the myth of Prometheus, the titan who defied the gods and gave fire to mankind. For this act, he was punished eternally, chained to a rock while his liver was devoured daily by an eagle. In science, Promethium carries that same aura of defiance, of unnatural fire, of something not meant to be where it is. And that's what makes its presence in Przybylski's star so utterly mind-bending. Promethium, element number 61 on the periodic table, is a rare earth element, part of the lanthanide series. But unlike its chemical siblings, Promethium has one critical distinction: none of its isotopes are stable. Not one. Every known form of promethium is radioactive, with relatively short half-lives. The most durable version, Promethium-145, has a half-life of just 17.7 years. That's a blink of an eye in the life of a star. Another isotope, Promethium-147, decays even faster, with a half-life of only 2.6 years. Now think about what that means. If you were to place a chunk of pure promethium in space and walk away, most of it would be gone in just a few decades. The atom would transmute, decaying into other elements as its unstable nucleus shed particles to achieve a more stable state. Eventually, there'd be no promethium left. Just its decay products. It doesn't linger. It doesn't wait. So how in the universe is it showing up in the outer atmosphere of a star? Because that's exactly what was found in the light spectrum of HD 101065. Using spectroscopy, astronomers observed clear and repeated evidence of spectral lines corresponding to promethium, those very specific atomic fingerprints that indicate its presence in the star's atmosphere. Not buried deep in the core, but dancing in the light that reaches Earth, 355 light-years away. It's important to emphasize this: promethium doesn't just appear by accident. It isn't something you find lying around. It has to be made. On Earth, we produce it synthetically in nuclear reactors, usually by bombarding neodymium or uranium with neutrons, a process that requires careful control and highly energetic environments. Even then, the amount produced is minuscule, measured in grams, and it's typically used in extremely specialized applications, like atomic batteries or certain scientific instruments. We certainly don't find it in nature in significant quantities. So how is it being produced in a star? What mechanism could possibly generate such a fragile, short-lived element, and keep generating it continuously? Because that's the only explanation that makes sense. If promethium is visible in the star's spectrum today, it must have been freshly produced, over and over again. Otherwise, it would have decayed long ago, especially considering that the light we're seeing left the star more than 350 years ago. In cosmic terms, that's like finding a lit match in a room that's been sealed for centuries. There are only a few natural processes we know of that can create promethium. One is the S process, slow neutron capture, which occurs in aging stars like red giants. Another is the R process, rapid neutron capture, typically associated with supernovae or neutron star collisions, extraordinarily violent events that scatter heavy elements into space. But Przybylski Star is not a red giant. It's not exploding. It's not merging with a neutron star. It's not undergoing the kind of turmoil required to forge promethium naturally in bulk. And even if it were somehow producing it deep within its core, it would be extraordinarily difficult for promethium to survive the journey to the outer layers of the star before decaying. That's like trying to carry an ice cube from the center of a volcano to the mountaintop without it melting. So the question becomes, what force is sustaining the presence of promethium in this star's atmosphere? Some astrophysicists have suggested that maybe there's a very specific, narrow shell inside the star where just the right conditions exist for promethium to be created via neutron capture and transported almost immediately to the surface. But this stretches known stellar models to their limits. It would require finely tuned magnetic fields, unusually low convection, and a system of element stratification that borders on precision engineering. Which brings us to the next problem. This isn't just a single anomaly. If this was a quirk of stellar chemistry or a rare internal process, you'd expect to see it in other stars too, at least occasionally. But to date, no other star has shown this unique promethium signature. Przybylski Star stands utterly alone. That isolation makes the discovery even more suspicious. Is it a 1 in a trillion natural accident? Or is it evidence of something far stranger? Because here's a deeply unsettling thought. On Earth, promethium is only found where we make it. We know it exists in nature only in trace amounts, typically as a decayed product of uranium, but never in quantities large enough to detect spectroscopically, not even on Earth. The only time we see it clearly is when we've manufactured it ourselves. When we've made a choice to produce it. Which leads to the question no scientist wants to ask publicly, but many have whispered in private: what if someone, or something, is manufacturing it in this star? It sounds absurd, until you realize that producing promethium requires an understanding of nuclear physics, intentional reactions, controlled environments. It's not the kind of thing that just happens. And seeing it glow in the spectrum of a distant star, one otherwise too mundane to be exploding or collapsing, feels eerily close to discovering a signature of technology. A trace of deliberate interference. Could it be an artificial marker? An alien equivalent of graffiti? A scientific experiment? Or perhaps, the remnants of some unimaginable stellar-scale engineering? Some theorists have gone as far as to suggest that promethium could be part of a stellar energy harvesting system, used to store or regulate radiation in some highly advanced fusion or fission process. Others have speculated that it might be a byproduct of alien element synthesis, an intermediate step in the creation of even heavier materials not known to us. And then there's the symbolic interpretation. If you were an intelligent species trying to signal your presence using the laws of physics themselves, what better way than placing a synthetic, radioactive, Earth-known element into a natural star? One we could see and recognize, but not explain. We don't have answers. Only theories. Most scientists still lean toward exotic but natural processes, some combination of magnetic diffusion, element stratification, and slow neutron capture. But the Promethium problem persists. It's still there. Still glowing. Still impossible. Promethium is more than just a chemical oddity in Przybylski Star, it is a cosmic paradox. A radioactive whisper from across the void. A sign of creation that defies decay. And whether it's the work of a star's strange chemistry or the signature of an intelligence far beyond ours, one thing is clear. Promethium should not be there. And yet it is. As if the presence of Promethium wasn't strange enough, Przybylski Star continues to unravel into deeper layers of mystery. Because Promethium, while shocking, isn't alone in this stellar puzzle. It's simply the first flag, one that has led astronomers into a chemical landscape even more bizarre, one that seems to be littered with other short-lived, unstable elements. The deeper scientists looked, the weirder the composition became, almost as if the star's spectrum was a collection of forbidden artifacts. Following Promethium, the next most intriguing suspect is technetium, element 43 on the periodic table. Like Promethium, technetium has no stable isotopes. On Earth, it's typically created as a byproduct of nuclear reactors or during the fission of uranium-235. Its most stable isotope, technetium-98, has a half-life of about 4.2 million years, much longer than Promethium, but still a fleeting moment in the life of a star. The isotope technetium-99, often used in medical imaging, has a half-life of just 211,000 years, which might seem long by human standards, but it is only the blink of an eye in stellar evolution. Here's why that's important. Even though technetium has been detected in some red giant stars before, it usually shows up in very specific late-stage stars undergoing a process called the slow neutron capture process, or S process. That's when a star becomes old and bloated, and its core starts generating free neutrons that slowly get absorbed by atoms, creating heavier elements. In such stars, technetium is created in real time, and carried to the surface through convective mixing, a sort of stellar churning that dredges up materials from deeper layers. But HD 101065 doesn't fit that profile. It's not a red giant. It's not in that advanced, turbulent stage of its life. It's a chemically peculiar star, an AP star, with strong magnetic fields and relatively stable, non-convective layers. The usual dredge-up process that explains technetium in red giants simply doesn't apply here. There's no obvious mechanism to produce it in the core and then deliver it intact to the outer atmosphere where we can detect it. It's as if technetium simply appears, unsupported by any reasonable astrophysical process. And then there are the actinides. The actinide series on the periodic table includes some of the heaviest and most radioactive elements known to science: thorium, uranium, plutonium, and their lesser-known relatives like curium, americium, and berkelium. Most of these elements are either highly unstable or extremely rare in nature. Some are only produced in nuclear reactors or as the result of nuclear explosions. Their presence in a stellar environment would be considered extraordinary, bordering on impossible. But in the case of Przybylski Star, some researchers have suggested the presence of spectral lines that may correspond to thorium, uranium, and even speculative matches for plutonium or other transuranic elements. That is, elements beyond uranium, with atomic numbers higher than 92. These include some of the most exotic materials ever synthesized in laboratories, many of which decay in seconds, minutes, or hours. Take curium-244, for example. It has a half-life of about 18 years, slightly longer than Promethium-145, but still far too short to be stable on astronomical timescales. Or americium-241, which has a half-life of 432 years, a blink of an eye compared to the lifespan of a star, which typically stretches into the billions of years. If any of these elements are truly present in Przybylski Star, they can't simply be leftovers from its formation. They must be actively produced, continuously replenished, sustained by some unknown process that keeps them from vanishing into oblivion through radioactive decay. Otherwise, we wouldn't see them. But let's step back for a moment and think about how improbable this is. transuranic elements don't just occur naturally in stars. In fact, we don't know of any stars that can synthesize elements like neptunium, plutonium, or californium under normal conditions. These elements, on Earth, were only created in the 20th century, often through meticulous and highly controlled reactions in nuclear laboratories. Their synthesis usually involves bombarding heavy nuclei with neutrons or other ions at high energies, processes that require extremely fine-tuned equipment and conditions. Yet in Przybylski Star, we might be seeing hints of them in the light it emits. This isn't like finding a peculiar isotope here or there. This is potentially an entire family of short-lived, laboratory-born elements populating the upper atmosphere of a seemingly ordinary star. And if true, it stretches the bounds of what natural processes can account for. The scientific response to this has been cautious. No one wants to jump to conclusions based on uncertain spectral matches. After all, spectral line identification is incredibly complex. Many elements have overlapping or similar lines, and rare earth elements in particular can crowd the spectrum with subtle variations. There's room for misidentification. There's room for noise. But even with those limitations, the evidence remains suggestive, strong enough that several papers have seriously entertained the presence of unstable or transuranic elements in the star's chemical makeup. And here's where things get even stranger. Unlike Promethium, which has a relatively simple spectrum, these heavier elements can create hundreds or even thousands of faint spectral lines, many of which aren't well documented even in our most complete atomic databases. If we're seeing these lines in HD 101065, and they don't match any known stable elements, we're left with two unsettling possibilities. Either we've underestimated the power of magnetic and nuclear processes in stars, or we're witnessing signatures of a process that's not natural. Some researchers have tried to explain the weird chemistry through radiative diffusion, a theory that suggests certain elements might migrate to the star's surface under the influence of radiation pressure and strong magnetic fields. In this view, even small quantities of rare elements, produced long ago or from surrounding interstellar material, could be pushed to the outer layers of the star and become more visible over time. But that still doesn't explain the presence of short-lived isotopes. Radiation pressure doesn't create elements. It only moves them around. So unless you start with a fresh supply of promethium, technetium, uranium, or plutonium, no amount of diffusion will make them appear in the spectrum. And let's not forget, these elements are radioactive. If they're present in high enough quantities to be seen clearly from 355 light-years away, they must exist in non-trivial concentrations. They must be abundant. You don't get that from a one-time fusion reaction or a freak event billions of years ago. You get that from something sustaining the reaction, again and again, for centuries. So what's fueling this impossible chemistry? Some propose that perhaps HD 101065 is sitting in the aftermath of a stellar explosion, a cloud of debris rich in exotic isotopes left over from a neutron-star merger or a rare type of supernova. But again, the star doesn't appear to be in such a region. Its environment looks relatively calm. There's no evidence of recent cataclysmic events in its immediate vicinity. It's isolated, stable, and yet completely bizarre. Others go further, speculating that perhaps the star is being manipulated, used as a platform for elemental synthesis on a scale we can't comprehend. The notion that we may be looking at a kind of stellar laboratory, where extreme energies are harnessed to create elements that we struggle to replicate even in our most advanced reactors. Because if someone, or something, wanted to show off technological prowess, or send a message across the stars, there are few signals more unmistakable than a radioactive element with a short half-life glowing in a star's atmosphere. A natural process might explain one or two anomalies. But an entire suite of unstable elements? That's a different story entirely. The deeper we fall into the mystery of Przybylski Star, the more we are forced to confront a question that should, by all rights, be absurd. How can synthetic elements, atoms that we ourselves only learned to create through decades of nuclear experimentation, be appearing naturally in a star? Synthetic elements. Just the term evokes laboratories, precision instruments, the slow churning of cyclotrons and reactors. These are not materials we mine from Earth or stumble upon in the wild. They're born in environments of deliberate violence, smashed into being by particle accelerators or forged in the controlled chaos of nuclear reactors. And yet, here they are, shimmering in the spectral light of a star 355 light-years away. When we talk about synthetic elements, we're usually referring to those beyond uranium on the periodic table, the transuranics. Plutonium, americium, curium, berkelium, californium, names that sound like they belong in the inventory of a science fiction arsenal. But many of these have reportedly shown up, or at least hinted at, in the spectral analysis of HD 101065. The implications are staggering. To fully appreciate the gravity of this, it's important to understand what synthetic actually means in a scientific context. It doesn't mean the element is artificial in essence. It means that it is not known to occur naturally in the observable universe in any significant amount. It has to be made. And not just made, forced into existence under very specific conditions. Take plutonium, for example. On Earth, we synthesize plutonium-239 in nuclear reactors by bombarding uranium-238 with neutrons. This isn't a simple or spontaneous event. It requires human engineering, fine control, and carefully maintained environments. The entire process is energy-intensive, dangerous, and highly regulated. And even when successful, the resulting element is fragile, unstable, and prone to decay. The same applies to americium, curium, and nearly every other synthetic element. They don't naturally accumulate. They can't survive the heat of a stellar core. And they certainly don't exist in any meaningful quantity unless someone, or something, put effort into making them. So here is the paradox at the heart of Przybylski's star. How can a star, which we assume to be a natural object, contain fingerprints of elements that only appear through artificial synthesis on Earth? The first hypothesis is, of course, the most cautious. Some astronomers suggest that these elements aren't actually there, that perhaps we're misreading the spectrum. The data might be contaminated, or the spectral lines may be overlapping with those of known, stable elements. In spectroscopy, especially with complex stars, the spectra can be crowded. Hundreds, even thousands of absorption lines can stack together, forming a web of signals that's difficult to disentangle. It's easy to mistake one signal for another if you don't have a perfect atomic database to reference. But the problem is, we do have atomic data for many of these elements. And the lines don't lie. Multiple independent analyses, spanning decades, using increasingly sensitive instruments, have consistently identified features that match known lines for promethium, technetium, and heavier transuranics. These aren't random glitches or one-off detections, they are persistent, observable signatures. So, if it's not a misreading, we have to look for natural explanations. One idea is that perhaps these synthetic elements aren't synthetic after all, but rather the product of rare astrophysical processes that mimic our nuclear laboratories. Maybe neutron star collisions or supernovae occasionally produce these elements, and some of the debris was swept up by Przybylski's star during its formation. In this view, the star is a collector of cosmic fallout, born from a cloud of interstellar dust already rich in radioactive leftovers. But this, too, raises a problem: decay. The half-lives of these elements are far too short. Even plutonium-244, one of the most long-lived transuranics, has a half-life of just 80 million years, tiny in stellar terms. Most of the others decay in decades, or even minutes. If the star formed billions of years ago, any radioactive elements present in its birth cloud would have vanished long before we had the chance to observe them. The timeline simply doesn't work. Some have proposed that perhaps cosmic rays or rare fusion processes in the star's magnetosphere could be producing new isotopes in tiny amounts. But again, these processes would require incredibly precise conditions, powerful neutron bombardments, sustained energy input, and carefully maintained environments. Not to mention, they would have to occur continuously, or the elements would vanish almost immediately through radioactive decay. All of this begins to stretch credibility. That's when the conversation starts to shift. Not into fantasy, but into speculative physics. What if these elements aren't natural, What if they were placed there? What if HG101065 isn't just a star, it's a machine, a laboratory, or even a message? It sounds like science fiction, but think about it. If a highly advanced civilization wanted to announce its presence to the universe in a way that any scientifically advanced species would eventually notice, what would they use? Radio signals degrade over distance. Megastructures might be hard to detect. But elements? Those are universal. The periodic table is the same everywhere in the cosmos. A civilization could use synthetic, short-lived elements, ones known to be extremely difficult to produce, as signatures, deliberately placed in a star's atmosphere to stand out to any intelligent observer. No natural process we know of explains them fully. Their presence would raise questions. And eventually, those questions might lead back to the ones asking them. If you can engineer at the scale of a star, if you can manipulate stellar magnetic fields, neutron flux, and fusion reactions, you could, in theory, design a spectrum, a fingerprint, a code. Promethium, technetium, curium, plutonium, each one a letter, a symbol, a message embedded in light. Of course, there are still other natural explanations on the table. Perhaps the star has unusual internal processes we simply don't understand. Maybe magnetic diffusion is more powerful than we realize. Maybe the rare elements are generated in a thin shell by strange quantum effects. Maybe. But every maybe is an admission of ignorance. A placeholder. A shrug dressed in equations. And meanwhile, the spectrum doesn't change. The lines are still there. The impossible elements are still visible. Every photon of light from HG101065 still carries with it the signature of atoms we thought belonged only to the hands of intelligent beings. So we're left with a chilling question, echoing across light years, encoded in spectral lines. Are we witnessing the work of nature, or the whisper of something intelligent? At some point, every natural explanation begins to fray. You can only stretch stellar models so far. You can only twist theories of magnetic diffusion, rare neutron capture, or element stratification so many times before the argument begins to feel strained, patched together more by wishful reasoning than empirical consistency. That's when a new possibility begins to take root, not out of desperation, but out of pattern recognition. A possibility that, for decades, hovered on the fringes of serious scientific discourse but now refuses to be ignored. What if HG101065 is not a natural anomaly at all? What if it is artificial? It's an idea both exhilarating and terrifying, that a star could bear the fingerprints of intelligence. That what we are observing through our telescopes is not just an eccentric cosmic object but a deliberate construction, or modification, by a civilization far more advanced than ours. Perhaps even a message. Not in words, not in symbols, but in chemistry, in the periodic table itself. This isn't an entirely new idea. In fact, the concept of astroengineering, that a sufficiently advanced civilization could alter stars themselves, has long existed within the framework of the Kardashev scale, which measures technological advancement based on a civilization's ability to harness energy. A Type 2 civilization on that scale would be able to control the energy of an entire star. Not just passively absorb its light like a solar panel, but actively manipulate it, change its processes, redirect its output, reshape its very nature. And here we are, staring at a star that seems to defy the laws of nuclear decay. Because that's what makes Przybylski Star such a unique candidate for this hypothesis. It's not just strange, it's singularly strange. There are thousands of chemically peculiar stars in the universe, and many exhibit odd elemental ratios. But none have been found with the same bizarre abundance of unstable and synthetic elements in their spectrum. If this were a normal, albeit rare, natural phenomenon, we would expect to see more examples by now. We'd expect some kind of stellar family or subclass that shares these traits. Instead, what we find is isolation. One star. One signal. One potential artifact. The alien hypothesis doesn't suggest little green beings are flying around inside the star. Rather, it proposes that perhaps an advanced intelligence has engineered the outer layers of the star, or is actively injecting elements into it, to serve a purpose we don't yet understand. Consider the logistics of this. A civilization capable of such feats would need to understand nuclear physics at a level we can barely conceptualize. They'd have to manage particle collisions, neutron fluxes, decay chains, and magnetic stratification with surgical precision. They would need machines the size of planets, or even larger. Perhaps automated systems designed to function for millions of years. Stellar-scale machinery indistinguishable from natural forces to anyone not looking closely. To us, this would be science fiction. But to a civilization thousands, or even millions, of years older than ours, it might be as mundane as weather satellites are to us. One fascinating idea is that the star could be used as a display device, a way of making its presence known without broadcasting a radio signal that fades over time. Instead of speaking into the void and hoping someone is listening, an alien intelligence could embed a persistent spectral anomaly into a star's light, something odd enough that any technologically mature species would notice, and impossible enough that they would ask, "Who did this?" Because that's exactly what we're doing now. The alien signature theory also gains weight when you consider how universal the language of chemistry is. The periodic table is not subjective. It's not cultural. It's a function of quantum mechanics, the same throughout the universe. Every intelligent species that reaches a certain stage of scientific development will understand atomic structure, nuclear decay, and element synthesis. It's inevitable. There's no need to translate a signal if you can use physics itself as the language. And so the question becomes, what would an alien's signature look like? Would it be some massive radio pulse beaming across the stars? A laser burst? A giant structure orbiting a star? Or would it be something more elegant, something that quietly stands out among the cosmos, patiently waiting to be noticed by the next species that learns to look at the stars not just for light, but for meaning? A star like Przybylski's, filled with elements that can't survive long, can't arise naturally in such quantity, and can't be explained by the models we use to understand the universe, might be exactly that kind of message. Not a voice. Not a transmission. But a persistent enigma, a puzzle carved into starlight. Skeptics, of course, resist this line of thinking. And they should. The burden of proof for such a claim is immense. Extraordinary claims demand extraordinary evidence. But here's the thing, we don't yet have an ordinary explanation. And the longer that gap persists, the more plausible the extraordinary begins to seem, not as fantasy, but as a working hypothesis. Some have even proposed that perhaps the star is not natural at all, that what we're seeing isn't a star in the traditional sense, but something masquerading as one. A reactor, a beacon, a cosmic lighthouse built by a civilization that has moved on from planets and now lives among machines and stars. A place where materials are synthesized not in laboratories but in controlled stellar furnaces. In this scenario, the presence of synthetic elements wouldn't be a byproduct. It would be the point. Because let's face it, if humans can already create promethium, plutonium, and californium in small amounts, with our relatively primitive technology, imagine what could be done by a culture with millions of years of progress ahead of us. Imagine what they could do with stars. And now imagine that they left a calling card. Glowing. Radiating. Waiting. In a star that shouldn't exist. One of the most puzzling, and frankly, damning, pieces of evidence against any natural explanation for Przybylski Star is the simple fact that the elements we observe in its spectrum should not be there anymore. Not now. Not ever. We're talking about materials that don't just decay, they vanish. Fast. Promethium, for example, has no stable isotopes, and its most enduring form, Promethium-145, decays in about 17.7 years. That's less than a quarter of a human lifetime. And yet we see it shimmering in the spectral light of HD 101065, a light that left the star over 350 years ago. Which means that even back then, centuries ago, promethium was present in its atmosphere in enough quantity to be observable from Earth. It should be gone. And it's not just promethium. Let's go through a few of these anomalous elements and consider their decay timelines, and by extension, how absurd it is that they are detectable at all. Take technetium. Its isotopes, such as technetium-98, have half-lives of just 4.2 million years, which might sound long, but it's a blink in stellar terms. HD 101065 is hundreds of millions, possibly billions of years old. Any technetium it could have formed with would have disappeared long before Earth even existed. And yet, spectral lines in its light strongly suggest technetium is present in the star now. Then there's plutonium-244, sometimes cited in speculation about Przybylski Star. This isotope has a longer half-life, about 80 million years. Long for a radioactive element, but still short enough to require recent replenishment if it's to be seen today. And anything with a shorter half-life, like plutonium-239, 24,100 years, americium-241, 432 years, or curium-244, 18 years, would be outright ridiculous to find unless it were being produced in real time. Yet suggestions of spectral matches to these materials have cropped up in analyses of this star. And then we have the really short-lived stuff. Some of the transuranic elements suspected, like californium-252, half-life, 2.6 years, or even more exotic elements like berkelium or einsteinium, decay in mere days or weeks. Let that sink in. The light from Przybylski's star that we are observing today began its journey toward Earth around 1670, long before electricity, modern chemistry, or even the idea of atoms as we know them. For those elements to appear in that starlight, they would have had to be present and visible on the star's surface at the time that light was emitted, more than 3.5 centuries ago. And yet, their natural half-lives wouldn't even carry them through the decade. This isn't a small discrepancy. It's not the result of rounding errors or observational noise. The math is brutal and unrelenting. These elements should be long gone. Even if they were somehow formed during the star's birth, or delivered to it by cosmic events, they wouldn't stick around. They'd decay, and fast. So either we are continuously misidentifying these spectral lines, and not just once, but repeatedly over decades of analysis, across different observatories, with varying instruments, or these elements are being made continuously, replenished, maintained. In other words, there has to be a mechanism. And that's the real mystery. What natural process in this star could possibly be creating radioactive isotopes on a continual basis without destroying them in the process? It's not fusion. Not the kind we know. Stars fuse hydrogen into helium, and in later stages can go on to create heavier elements, carbon, oxygen, neon, silicon, and eventually iron. But after iron, things get complicated. Fusing heavier elements starts consuming more energy than it produces. That's why even the largest stars don't naturally create plutonium or curium in any great quantity. They don't have the energy budget for it. And even in extraordinary events like supernovae or neutron star collisions, which do produce heavier elements through the R process, rapid neutron capture, the products don't linger in a stable environment. They're flung into space as debris and scattered across the galaxy. They don't settle calmly on the surface of a chemically peculiar star. HD 101065, however, shows none of the telltale signs of recent violent events. It isn't the shattered core of a past explosion. It's not a remnant in a neutron-rich cloud. It sits quietly in its region of the Centaurus constellation, giving no indication of catastrophic origin. And yet, the evidence remains. The elements in its atmosphere are decaying too quickly to be natural, unless they are constantly being created. Which leaves us with two choices. Option 1, there is some truly unknown stellar mechanism at work, one that operates with incredible precision to generate rare, radioactive isotopes, elevate them to the star's outer layers, and keep them visible for hundreds of years. A mechanism that has never been observed in any other star. Or, Option 2, we are not looking at a natural process at all. We're looking at a maintained system. One where the decay of promethium or curium is not a terminal point, but a cycle, a process that is deliberately renewed. In this view, the presence of these short-lived elements isn't a puzzle, it's a clue. A marker of activity. A living signature. Just imagine it, an alien system designed to inject promethium into a star at regular intervals. Not because the element is useful in any mundane way, but because it's a beacon. A flashing light. A radioactive flare that says, "Look here!" Because from a cosmic perspective, promethium is a terrible choice for anything long-term. It's not stable. It decays quickly. It's dangerous. It glows, but not for long. And yet, perhaps that's the point. If you wanted to grab the attention of any civilization just reaching the point where they can study stars in detail, where they can analyze spectral lines and recognize what doesn't belong, what better way than to embed something that shouldn't be there? A synthetic element. A self-destructing message. One that requires constant care to remain visible. And one that guarantees this chilling realization. Someone is keeping the fire alive. By astrophysical standards, not all stars are created equal. Many conform neatly to categories based on temperature, size, color, and composition. These categories, like the well-known Obafm sequence, help us understand how stars behave, how they age, and what they're made of. But some stars seem to veer off this predictable path entirely, slipping through our classifications like a puzzle piece from the wrong box. One such category is that of chemically peculiar stars, a class of objects that stubbornly refuse to follow the rules. Among them, HD 101065, also known as Przybylski Star, doesn't just break the mold, it shatters it. To begin with, let's demystify the label. Chemically peculiar stars, often abbreviated as CP stars, are stars that show unusual abundances of certain elements in their spectra. Some have too much silicon, others too much mercury, manganese, or europium. Their light betrays an imbalance, sometimes mild, sometimes extreme, when it comes to their chemical content. They're divided into subgroups, and one of the most intriguing among them is the group known as AP stars. The A in AP stands for their spectral type. A-type stars, which are white or bluish-white, relatively hot, and usually show strong hydrogen absorption lines. The P stands for peculiar. That means the star exhibits strong or unusual lines of certain elements, like strontium, chromium, or the rare earth metals, while showing weak or even absent lines for others. What causes these anomalies? In many cases, it's a mixture of slow rotation, stable atmospheres, and extremely strong magnetic fields. These ingredients create an environment where radiative diffusion, a subtle process by which radiation pressure pushes certain elements upward while gravity pulls others downward, can act without interruption over long periods. The result is a surface that's been chemically sorted, like a stratified lake where layers of different materials settle into place. HD 101065 fits into this AP category, but only barely. It's not just chemically peculiar, it's chemically defiant. For most AP stars, we might observe an excess of certain elements, say, an unusually high abundance of silicon or chromium. But Przybylski Star takes that to an entirely new level. It doesn't just have more of certain elements, it seems to host elements that don't even belong in a star at all. Whereas most chemically peculiar stars might show enhancements of elements like strontium or europium, HD 101065 goes so far as to display the possible presence of promethium, technetium, neptunium, and a gallery of actinides and transuranic elements. These are not just rare, they're radioactive, unstable, and in many cases, unknown in any natural setting outside of supernovae or laboratory reactors. What's more, the hydrogen lines in HD 100 and 1065 spectrum are unusually weak, even though it should be a hydrogen-burning star by nature. This suggests that not only are the chemical ratios on the surface completely out of balance, but also that the most fundamental building block of stellar energy, hydrogen, is somehow underrepresented in its outer layers. That's not just peculiar. That's wrong. It implies that something is fundamentally different about how this star operates, or at the very least, how its surface presents itself. And if that weren't strange enough, the star's magnetic field is off the charts. Most AP stars are magnetically active, but Przybylski's star has a magnetic field strength in the range of thousands of Gauss, several hundred times stronger than Earth's own magnetic field. This immense force isn't just a footnote, it's a possible driving factor in the strange distribution of elements we see on its surface. The magnetic field can trap ions, prevent convective mixing, and create vertical stratification zones where elements can accumulate or deplete over time. But even magnetic fields have their limits. Magnetism and radiative diffusion might explain the presence of some rare Earth elements. They might even allow for the sorting of heavier atoms toward or away from the surface. But they cannot explain the continuous presence of rapidly decaying radioactive elements. There's no version of this theory that allows for californium or einsteinium to simply linger on the surface for decades, especially not in a star that's millions or billions of years old. In fact, that's one of the most damning strikes against purely natural theories for HD 101065. While the AP classification offers a partial explanation for its behavior, it can't account for the specific set of anomalies this star exhibits. It's like calling a black hole dense, technically true, but missing the overwhelming gravity of the problem. In some ways, you could argue that HD 101065 has outgrown the AP classification entirely. It's in a league of its own. A chemical zoo without precedent. An isolated specimen that stubbornly exists outside the standard script of stellar evolution. This isolation is what makes Przybylski Star so powerful as a candidate for deeper investigation. If we saw hundreds of stars like it, we'd develop a subclass, a theory, and probably a mundane explanation. But we don't. We only have one. And it breaks nearly every rule we have. So what do you do when a star doesn't just stretch your models but breaks them repeatedly? You pay attention. You consider the possibility that it might not be just peculiar, but constructed. That perhaps the weirdness isn't a bug. Perhaps it's the point. Because if you're looking to send a message to intelligent life somewhere in the universe, there may be no louder whisper than a chemically peculiar star, a real one, with real mass, real gravity, and real nuclear fusion, coded not in binary or beams, but in atoms. Atoms that shouldn't exist in nature. And yet, here they are. Among all the strange features of Przybylski Star, one in particular strikes at the very heart of what we think a star is. Its unusually weak hydrogen lines. For most stars, especially those in the A-type classification like HD 101065, hydrogen is the dominant element, the fundamental fuel source, the baseline of stellar identity. And yet, when we observe this star's spectrum, hydrogen, the lightest, most abundant element in the universe, barely shows up. That's more than a curiosity. That's a red flag. Because stars are not made of exotic elements like europium or promethium. They are born of hydrogen, fuse hydrogen into helium, and ultimately die once hydrogen runs out or fusion becomes unsustainable. When we point our spectroscopes at the sky, the hydrogen lines in a typical star blaze with clarity. The Balmer series, with its signature H-alpha, H-beta, and H-gamma lines, is one of the most consistent, recognizable fingerprints in all of astronomy. But in Przybylski Star, those lines are strangely muted. To understand why that's so alarming, we need to look at how stellar atmospheres work. In a star's outer layers, light emitted from the core passes through different elements on its way out. These elements absorb specific wavelengths, leaving behind dark, absorption lines, in the spectrum. The strength of those lines tells us not only what elements are present, but in what quantities, and how active they are. In almost every main sequence star, hydrogen dominates both in abundance and spectral intensity. Even chemically peculiar stars, those classified as AP or AM, still show strong hydrogen lines, even as other elements fluctuate wildly. But HD 101065 defies this trend. Its hydrogen lines are so faint that some early observers initially doubted its classification as an A-type star at all. It was unlike anything seen before. Over the decades, refinements in spectral resolution and data analysis have confirmed that hydrogen is present, but not in the strength expected for a star of its temperature and spectral class. It's as though the star is cloaking its hydrogen, or perhaps displacing it, allowing other, heavier elements to dominate the spectral landscape. This leads to a series of uncomfortable questions. Is there something about HD 100 and 1065's outer atmosphere that causes hydrogen to sink inward, away from the visible surface? This could, in theory, be explained by diffusion mechanisms or magnetic stratification, where strong magnetic fields and radiative forces push lighter elements down and pull heavier ones up. But again, this is a process we only see in specific cases, and never with such extreme effects. Or is the hydrogen there, but somehow not active enough to emit strong spectral lines? That would imply a change in the temperature, pressure, or ionization levels in the outer layers of the star, changes that should, in turn, affect other lines as well. But they don't. The lines of exotic metals remain strong and clear. It's only hydrogen that's diminished. The oddity becomes even more baffling when you consider that the Balmer lines are strongest in stars that have surface temperatures between about 7,500 and 10,000 K, right where HD 101065 resides. This star should be a hydrogen beacon. Instead, it's whispering. Another explanation could be external contamination, a surrounding envelope or shell of material blocking or absorbing the hydrogen light. But there's no evidence of a dust cloud or circumstellar disk thick enough to selectively mute only hydrogen. And even if such a structure existed, it should also obscure other spectral features, yet the rare earth metals remain untouched. So, what's going on? Here's where speculation steps into the void. One radical idea is that the weak hydrogen lines are not the result of a natural process at all, but of intervention. If some intelligence is deliberately altering the outer layers of the star, injecting synthetic elements, managing its surface chemistry, they may have found a way to dilute or suppress hydrogen visibility. Why? Because in doing so, they're breaking a universal rule. And that's the point. It's a signal. If every A-type star in the universe obeys the same rules, strong hydrogen lines, standard fusion processes, predictable evolution, then the best way to stand out is to violate those rules in a way that no natural process could. It's the cosmic equivalent of rearranging the stripes on a zebra, or flipping the colors of a traffic light. Anyone who understands the system will instantly recognize that something's wrong. And Przybylski's star is definitely wrong. Could the suppression of hydrogen be part of a communication strategy? A sort of elemental cipher? If a star's chemical spectrum is a message, then muting hydrogen could be the first letter, the thing that says, "Pay attention." Or perhaps it's part of a cloaking mechanism, meant to hide the true nature of the star's interior processes. Hydrogen, being so abundant and active, tends to dominate the optical fingerprint. If you wanted to show off exotic materials without interference, you'd have to get hydrogen out of the way. Not physically remove it, just hide it from view. Either way, the implications are unsettling. Because whether it's a natural anomaly or an engineered feature, weak hydrogen lines in a hydrogen-burning star are like finding a car engine that doesn't smell like fuel. It forces you to ask, what's really powering this thing? And that's what Przybylski's star continues to confound. Every time we think we've nailed down one aspect of its strangeness, another one emerges. And like all good mysteries, the real answers might lie just beneath the surface, hidden behind an atmosphere that, for reasons unknown, refuses to let hydrogen shine through. When a star behaves in ways that baffle astrophysicists, when it defies chemical expectations, glows with impossible elements, and whispers secrets in spectral lines, it's only a matter of time before someone at SETI takes notice. And sure enough, Przybylski's star, with all its radioactive riddles and missing hydrogen, has not escaped the gaze of the search for extraterrestrial intelligence. SETI researchers are trained to look for anomalies. But more than that, they're trained to distinguish between anomalies that are natural but rare, and those that might hint at intentionality, patterns, arrangements, or energetic signatures that suggest purpose rather than accident. In the early decades of SETI, the focus was squarely on radio signals, the idea that intelligent civilizations would transmit information via the electromagnetic spectrum, perhaps hoping that others, like us, would listen. But as our own understanding of physics and cosmic phenomena deepened, the scope of SETI began to evolve. What if civilizations don't send signals? What if they simply leave artifacts? What if they alter natural bodies, asteroids, moons, or even stars, in ways that could be noticed by those with the right tools and enough curiosity. That's why a star like HD 101065 eventually caught SETI's attention. It didn't happen immediately. Back in 1961, when Antoni Przybylski first discovered the star's strange composition, the tools to even speculate about extraterrestrial engineering were rudimentary at best. But as more spectroscopic data accumulated, decade after decade, and the list of unexplainable features grew longer, something shifted. The anomalies stopped being statistical noise. They became a pattern. It was in the late 20th and early 21st century that researchers within the SETI community began to quietly murmur about HD 101065. Papers didn't headline the word alien, of course. SETI scientists are careful, scientific credibility demands it. But behind closed doors and in speculative discussions, Przybylski's star was added to the short list of cosmic objects that might deserve a second look. Not for a radio pulse. Not for a laser flash. But for something more subtle. Because the star's signature wasn't just rare. It was unique. The synthetic elements detected in its atmosphere couldn't be explained by known stellar processes. They were too heavy, too unstable, too transient. And yet there they were, persisting across decades of observations, as if someone, or something, was replacing them, maintaining them, or manufacturing them in real time. For SETI researchers, this raised a provocative possibility. What if Przybylski's star is an engineered beacon? Not in the traditional sense of a signal broadcast across the stars, but in the form of a physical message embedded in atomic structure. The kind of message that would be instantly understood by any civilization that had mastered spectroscopy, built observatories, and studied the periodic table. Because while languages differ, and cultures vary, the laws of quantum mechanics and nuclear decay are universal. Any advanced species will understand that promethium decays quickly. That californium doesn't last. That the heavy transuranic elements have no place on a stellar surface, unless someone put them there. It's a message in pure logic. A message that says, "You're not alone." SETI researchers began quietly modeling scenarios. How could such a beacon be created? Would it require stellar-scale megastructures? Could strong magnetic fields be used to trap isotopes in stable layers? Could artificial injection systems, akin to orbital accelerators or magnetically guided plasma streams, seed the stellar atmosphere with precise isotopic cocktails? These ideas weren't published in mainstream astronomy journals. But they found homes in white papers, conference back channels, and closed-door meetings among interdisciplinary researchers. SETI isn't just a listening post, it's a network of thinkers considering what alien technosignatures might actually look like, beyond just radio and light. And here was a star, glowing with the fingerprints of nuclear engineering, exhibiting none of the normal stellar behaviors one might expect of an A-type star, and sitting 355 light-years away with an impossible chemical composition that had remained unchanged for decades. Some within SETI even proposed initiating active scanning of the region around HD 101065, pointing radio telescopes, optical detectors, and even infrared arrays at its location in hopes of picking up secondary signals or heat signatures that might correlate with the hypothetical presence of machines or structures. If a civilization is maintaining the isotopic profile of a star, perhaps they're doing it with technology that emits detectable waste heat, electromagnetic residue, or gravitational anomalies. Others cautioned against too much optimism. After all, many stellar mysteries in the past had turned out to be explainable. Pulsars, once considered possible alien signals, turned out to be neutron stars. Tabby's star, once suspected to host a Dyson swarm, was later attributed to dust clouds and dimming cycles. But the difference was clear. Przybylski's star wasn't pulsing. It wasn't dimming. It wasn't flickering strangely. It was simply wrong. Consistently wrong, unchangingly wrong. And in that persistent wrongness, some SETI researchers saw a kind of consistency, the signature of something more stable than chaos. The signature of control. So while the star doesn't dominate headlines or serve as a SETI flagship target, it lingers. A quiet mystery in the database. A curiosity that resurfaces whenever the conversation turns to what alien technology might look like when it's not trying to hide, but also not trying to shout. Something that waits patiently for us to become smart enough to see it. Something that trusts the science itself to carry the message across light years. In a field where silence is the norm, Przybylski Star remains a kind of whisper. One that, so far, no one has been able to silence or fully explain. When we think of alien megastructures, the first name that comes to mind is often the Dyson sphere, a colossal shell or swarm of structures built around a star to harvest its energy. Popularized by physicist Freeman Dyson in the 1960s, the idea captured the imagination of scientists and science fiction writers alike. A technological feat so advanced it would place its builders squarely in the realm of a Type II civilization on the Kardashev scale, capable of harnessing the total energy output of an entire star. But what if the purpose of such a megastructure wasn't simply to collect energy? What if it was to create matter? This brings us to a more speculative but increasingly discussed idea, the Dyson Forge. Imagine a civilization so advanced, so technologically mature, that it doesn't just build around stars, it uses them. Not as heat lamps or reactors, but as factories. Places where the fundamental particles of matter can be arranged, manipulated, and transformed under conditions no laboratory on Earth could ever replicate. Now look back at HD 101065, Przybylski Star. A star with unusually strong magnetic fields. A star with weak hydrogen lines. A star emitting the spectral signatures of radioactive elements, many of which are so unstable that they should have decayed long ago. In any other context, this would seem impossible. But what if it isn't? What if those unstable elements are not accidents, but products? The concept of a Dyson Forge suggests a megastructure, not built to surround a star for energy collection, but to manipulate its nuclear environment, funneling its immense heat, radiation, and magnetic forces into controlled nucleosynthesis, the process by which new atomic nuclei are created. Under normal conditions, stars produce heavier elements through fusion. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and so on, until iron. Beyond iron, stars cannot fuse elements without consuming more energy than they produce, which is why the actinides and transuranics are exceedingly rare in the universe. They form only in catastrophic events, supernovae or neutron star collisions, through what's called the R process, or rapid neutron capture. But in a Dyson Forge? Those limitations may not apply. If a civilization were able to harness the raw power of a star, not just its light, but its internal reactions, its magnetic architecture, and its particle flows, they could theoretically simulate, or even surpass the R process on a continuous basis. They could create elements like promethium, technetium, californium, einsteinium, and even hypothetical elements beyond our current periodic table. These elements, extremely valuable for advanced energy systems, exotic materials, or quantum applications, would be manufactured in stellar quantities. And what would be the byproduct of such engineering? Spectral anomalies. Exactly the kind we observe in HD 101065. Because here's the thing about synthesis at that scale, you can't hide it. If you're injecting neutron-rich isotopes into a stellar atmosphere, you're going to change its spectrum. You're going to leave behind radioactive fingerprints, promethium lines, technetium echoes, unexplained dips and peaks where no such features should exist. The universe doesn't keep secrets easily, especially when you're working with stars. So, the Dyson Forge theory begins to make sense as a lens through which we can interpret Przybylski Star, not as a broken object, but as a functional one. A device. A piece of technology. Maybe even an ancient one, still humming along without its creators, tirelessly churning exotic matter into being. If this theory holds water, then HD 101065 might not be alone. There may be other such forges out there, hidden in plain sight, indistinguishable from stars except for their bizarre chemistry. Perhaps we just haven't looked closely enough. Or perhaps this one star is doing something special, something unique to its mission. Maybe it's not just manufacturing rare elements. Maybe it's sending a message through them. Because let's imagine the psychology of such a civilization. They understand that stars are universal. They know that any species anywhere in the cosmos that reaches the level of spectroscopy will be drawn to stars like moths to light. What better way to catch their attention than to embed synthetic isotopes in the stellar spectrum? Not a transmission. Not a code. Just an impossible element, something that says, "This isn't natural." And so, a Dyson forge becomes more than a factory. It becomes a beacon. Of course, many will scoff at such speculation. The natural explanations, while incomplete, are often preferred. Diffusion, magnetic sorting, and rare nuclear processes are invoked. But none of them explain why so many short-lived radioactive elements would be visible, consistently, and in such strange proportions. None of them suggest an ongoing replenishment system, but a Dyson forge does. And if such a system exists, then we are not just looking at a star. We are looking at a monument. A stellar-scale machine, built not to hide, but to last. Its light not only illuminates, but speaks. It carries with it the unmistakable voice of purpose. Maybe, just maybe, HD 101065 is the forge. And its glow is the work of minds far older, and far more advanced, than our own. Let's follow the speculation deeper. If HD 101065 isn't a naturally occurring oddity, or at least, if nature alone doesn't fully account for its mysteries, then perhaps it's something else entirely. A nuclear laboratory on a cosmic scale. A place not just of passive fusion, like all stars, but of active nuclear experimentation. A stellar testbed. We know what it looks like when nature builds stars. We've watched them form in molecular clouds, burn through their hydrogen, collapse, flare, explode, die. Their life cycles are majestic but well modeled. And we know what fusion looks like in those stars, progressing predictably from hydrogen to helium to heavier elements, ultimately stalling at iron. Beyond that point, even the most massive stars collapse, unable to continue producing energy through fusion. That's the standard playbook. But HD 101065 doesn't seem to follow that playbook. Its surface contains elements that cannot be the products of ordinary stellar evolution, including actinides and transuranics, many of which have half-lives so short that they should vanish before the light they emit can even reach us. Promethium, technetium, neptunium, even possible traces of elements heavier than uranium. These materials are not supposed to exist in stars. Unless someone, or something, is making them there. Consider what it would mean to use a star not as a furnace for passive fusion, but as a controlled site for synthetic nucleosynthesis. Instead of simply relying on what fusion naturally produces, an advanced civilization might manipulate the stellar environment to encourage the creation of very specific atomic structures. This idea is not pure science fiction. Even our own primitive technology has hinted at such possibilities. In particle accelerators like the Large Hadron Collider, we've created exotic elements that don't exist in nature, some that live only for fractions of a second. We've triggered collisions that replicate, on the tiniest scale, conditions similar to those in the cores of stars or supernovae. Now imagine scaling that up to an entire star. The immense pressures, the temperatures, the magnetic fields, these are not obstacles. They are tools. A sufficiently advanced intelligence might see a star not as a distant light, but as raw potential. A system to be harnessed, tuned, and manipulated. And what better laboratory than one that already contains plasma, heat, and gravity wells beyond anything you could ever build artificially? They wouldn't need to build a particle collider. They'd build a star that is one. So what might be the goal of such experiments? One possibility, to create exotic matter. The kinds of elements needed for advanced energy systems, or materials for megastructures. Perhaps even elements that don't exist naturally anywhere else. Maybe they're testing the stability of super-heavy elements in real stellar environments. Maybe they're producing antimatter, strange matter, or quark-gluon plasmas to study phase transitions in nuclear physics that go far beyond our current knowledge. Another possibility, they're observing the limits of fusion itself. Seeing how far you can push a star's reactions before it destabilizes. Trying to ignite types of reactions that aren't part of normal stellar life cycles. What happens if you introduce a stream of neutrons into a stable star's outer layers? What isotopes can form under that bombardment? What happens to those isotopes over time? The third, and perhaps most chilling possibility, is this: they're not doing science. They're doing messaging. Maybe the nuclear anomalies aren't just byproducts, they're intentional markers. Just like we embed isotopic signatures in radioactive material to trace its source, maybe these alien scientists have left a chemical signature that says, "We were here." It's a calling card written in atoms. And unlike signals, which dissipate, or artifacts, which corrode, stars endure. A modified star can remain visible for centuries, even millennia, projecting its strange composition into the cosmos long after the experimenters are gone. So what does this mean for us? If HD 101065 is a nuclear testbed, then we are not just passive observers. We are, inadvertently, participants in an experiment we don't understand. Our telescopes become measuring instruments for someone else's lab. Every spectral line we analyze is a data point in a project whose scope and intent are beyond our comprehension. It also forces us to reconsider our definition of a natural star. Because if even one star in the galaxy has been manipulated, its chemistry altered, its fusion tailored, then the assumption that stars are untouched and unmodified becomes dangerous. We'd have to wonder how many others out there might also be artificial, or at least artificially influenced. Perhaps HD 101065 is the first of its kind we've noticed. Or perhaps it's just the most brazen. Because if you wanted your work to be seen, if you wanted to leave behind something no civilization could ignore, wouldn't you hide it in plain sight? Wouldn't you light up a star? On the surface, Przybylski Star appears calm, almost serene. Its luminosity is steady. There are no dramatic flares or erratic pulsations. It rotates slowly, gently radiating light that, to the untrained eye, looks no different from countless other A-type stars scattered across the galaxy. But that placid glow hides something potentially far more disturbing. Because what if the real action isn't on the surface at all? What if, beneath that deceptively tranquil shell, something wild is happening, a furnace far more chaotic, unstable, and extreme than any ordinary star of its class should possess? This is where we enter deeply speculative territory, but it's territory worth exploring. One hypothesis suggests that the bizarre, radioactive chemical signatures we observe in HD 101065 aren't just exotic accidents. They may be ejecta from violent internal activity, surfacing like toxic gases escaping from a deep ocean vent. And that activity could resemble, at least in some ways, what we see in the most extreme objects in the cosmos, neutron stars. To understand the gravity of this speculation, we need to revisit what makes neutron stars so unique. Neutron stars are the collapsed cores of massive stars that have gone supernova. What remains is an object so dense that its matter has been crushed into a state of degenerate neutron matter. Just a teaspoon of it would weigh billions of tons. Their internal physics are almost alien: superconductivity, superfluidity, incredibly strong magnetic fields, and pressure environments where quarks may no longer be confined inside protons and neutrons but exist in a free-floating plasma of subatomic chaos. These interiors are the ultimate nuclear laboratories, places where the known rules of physics begin to bend, and maybe even break. And some scientists have begun to ask, what if certain stars, like Przybylski Star, contain pockets or cores of similar exotic matter, not fully collapsed into a neutron star but also no longer purely classical in behavior? Could HD 101065 be undergoing partial collapse, a kind of slow-motion death spiral that hasn't yet triggered supernova, but is already producing hyperdense matter in its core? If so, that would explain a great deal. It would explain the production of heavy radioactive elements like technetium, promethium, and possibly even neptunium or plutonium, because these elements are thought to be forged during rapid neutron capture, our process, events that typically only occur in supernovae or neutron star mergers. But if something neutron star-like is happening internally, then HD 101065 might be generating these rare elements all by itself. It would also explain why the star's atmosphere is so chemically abnormal. Imagine shockwaves, bursts of neutron-rich plasma, or convective eruptions pushing these unstable materials from the chaotic depths to the visible surface. These elements wouldn't last long, many decay in minutes, hours, or days, but if the process is continuous, the supply line is always active. You wouldn't see this kind of surface chemistry unless something extraordinary was happening beneath it. And in HD 101065, we might be witnessing just that, a star with a calm mask and a chaotic heart. There are precedents for such internal mystery. Take the class of stars known as Thorn, Sitco objects, a theoretical type of star where a neutron star merges into the core of a red supergiant. From the outside, these stars look relatively normal, but deep inside, a degenerate neutron core may be injecting its exotic physics into the host star's envelope, producing strange element profiles that we might detect from afar. Could Przybylski's star be something similar? Perhaps not a Thorn, Sitco object in the classic sense, but a hybrid, a chimeric star whose internal structure includes a dense, neutron-rich anomaly, buried beneath layers of more ordinary stellar matter. Another possibility is that the star is undergoing episodic internal disruptions, akin to mini-supernovae or core quakes. These might not be energetic enough to destroy the star, but could be sufficient to alter its internal layering, eject exotic material, or create conditions where particles are accelerated to extreme energies, triggering synthetic nucleosynthesis. This would also help account for the star's magnetic field, which is extraordinarily strong even for an AP star. Magnetic fields are often the fingerprints of internal dynamism, churning plasmas, differentially rotating layers, or even magnetohydrodynamic instabilities could be amplifying magnetic forces from the chaotic core and transmitting their effects to the surface. That, in turn, could further sort or stratify elements, pulling the heavy and radioactive ones into zones where we can detect them. And here's the truly mind-bending part. If these internal processes are abnormal, then perhaps this star isn't in a stable phase of its life cycle at all. Perhaps it's dying, but in a way we've never seen before. Or worse, perhaps it's being used. Because if someone, or something, was experimenting with neutron star-like conditions, and they needed a naturally stable environment to contain those forces, what better crucible than a star? It already provides the heat, the gravity, and the pressure. All that's needed is the right insertion of exotic matter or catalysts, and the fusion machine becomes something much stranger, a reactor for nuclear innovation, hidden behind a veil of starlight. That calm glow we see from Earth may be the outer casing of a reactor we were never meant to notice. But we did. We noticed the spectral anomalies, the weak hydrogen, the impossible isotopes, the magnetic excess. And now, we must ask ourselves what's really going on inside HD 101065. Because sometimes, it's not the things we see that matter. It's the secrets they're hiding. At first glance, HD 101065 might seem like a quiet star, but lurking behind its faint hydrogen lines and exotic chemistry is something far more intense: magnetic fields of staggering strength. These aren't just a footnote in its profile, they may be central to everything strange about it. Because if you dig deep into the mechanisms that control a star's behavior, you'll find that magnetism has a way of rewriting the rules. Stars, by their nature, are fluid, dynamic spheres of plasma, and plasma is easily shaped and influenced by magnetic forces. In our own sun, magnetic fields drive sunspots, solar flares, coronal mass ejections, and the 11-year solar cycle. And those are in a star with a magnetic field of just a few Gauss on the surface. HD 101065, by contrast, has a surface magnetic field strength in the range of several thousand Gauss, on par with some of the most magnetically extreme stars ever observed. This places it in a special class of stars known as magnetic AP stars, chemically peculiar stars with strong, globally organized magnetic fields. These stars tend to rotate slowly, often exhibit spectral anomalies, and can display patches or spots of different chemical composition on their surfaces. But even within this rarefied category, Przybylski Star stands out as a complete enigma. To understand why its magnetic field might be so important, we have to consider what strong magnetism can do to the materials inside a star. First, it can interfere with convection, the process by which hot material from deeper layers rises to the surface and cooler material sinks. This convection is essential to mixing elements throughout the stellar interior. When magnetic fields become powerful enough, they suppress this mixing, allowing the surface to become stratified, layered in distinct bands of different elements. This could partially explain why Przybylski Star has such a bizarre chemical composition. Elements that should be deeply buried in the interior, heavy rare earths, radioactive isotopes, even transuranics, might be magnetically levitated into the outer layers. Meanwhile, lighter elements like hydrogen could be pushed downward or diffused away from the line of sight. Second, strong magnetic fields can trap charged particles. Much like Earth's Van Allen belts or Jupiter's powerful radiation zones, magnetic stars can create zones where ions are confined, spiraling around magnetic field lines. These zones can become element reservoirs, holding radioactive material near the surface, preserving elements that would otherwise decay too quickly to be seen. This matters profoundly in the case of elements like promethium or technetium. These are short-lived, radioactive elements with no stable isotopes. Finding them in a star is already shocking, but finding them reliably, over decades, is nearly impossible to reconcile with known stellar physics. However, if HD 100 and 1065's magnetic field is not just strong, but structurally stable, it could trap newly synthesized isotopes in place long enough for them to show up in our spectroscopic readings. Third, strong magnetic fields can help power localized nuclear reactions or concentrate energy in specific regions. In our Sun, magnetic reconnection events release immense energy during flares, energy capable of accelerating particles to near light speeds. Now imagine a magnetic field thousands of times stronger, anchored in a star already behaving abnormally. It's not impossible to imagine localized processes that might trigger fusion or transmutation in controlled regions. Some scientists have even speculated that magnetic fields may help mimic the rapid neutron capture, our process, normally seen only in supernovae. In these explosive environments, heavy elements are formed in a fraction of a second. Could HD 101065 be simulating that our process within pockets on or beneath its surface, aided by magnetic fields acting as stabilizers, accelerators, or funnels for particle flows? If so, that changes everything. It means the star could be manufacturing exotic isotopes continuously, and its magnetic field could be acting like the plumbing and containment system of a nuclear reactor, controlling reactions, preventing decay, and channeling byproducts into view. But here's where it gets even more intriguing. HD 100 and 1065's magnetic field doesn't seem to decay or change erratically over time. It appears to be stable, long-lived, and globally organized, like a permanent magnetic skeleton wrapped around a star. This goes against expectations for ordinary stars, whose magnetic fields are usually dynamic and chaotic. In this case, it seems engineered, or at least unnaturally persistent. That raises another question. Could such a magnetic structure be artificially enhanced? We know that magnetism is fundamental to all electric technologies. If a civilization wanted to manipulate a star, not just harvest its energy, but control its internal processes, they might start by altering its magnetic field. A strong enough field could shape convection, influence fusion zones, and even write chemical signatures into the spectrum visible from Earth. That idea starts to align with concepts like the Dyson forge, but with an important twist. Maybe the manipulation doesn't come from external megastructures, but from internal magnetic engineering. Maybe the star is being modified not with shells and satellites, but with carefully controlled magnetohydrodynamics. It's also worth remembering that magnetic fields aren't just powerful, they're silent. A modified magnetic field leaves no glowing machinery, no obvious waste heat, no flashing beacons. It just bends the plasma of the star into strange, unnatural patterns. So when we see spectral anomalies in Przybylski Star, rare earth elements, radioactive isotopes, absent hydrogen, we may not be seeing surface chemistry. We may be seeing the shadows cast by magnetic fields operating at levels far beyond our understanding. In essence, the star may be wrapped in invisible hands, shaping its emissions, controlling its layers, and perhaps hiding secrets deeper within. And all we have to go on is the ghost of those hands, curves in the light, cracks in the pattern, atomic footprints that don't match any known natural behavior. We might not yet know what HD 101065 really is. But one thing is increasingly clear. Its magnetism is not just an anomaly. It may be the key. When the light from HD 101065 first revealed its peculiar chemical makeup, an atmosphere seemingly polluted with rare earths and radioactive isotopes, scientists rushed to find natural explanations. After all, the principles of stellar evolution have served us well for decades. But Przybylski's star quickly became the outlier that refused to be explained by simple models. Still, not everyone jumped to alien megastructures or sentient stars. One theory that gained traction in the scientific community was diffusion, a natural process that could, in some cases, concentrate specific elements in a star's atmosphere due to gravity and magnetic fields. In basic terms, element diffusion refers to how particles in a star can move under the influence of different forces. Gravity pulls heavier elements inward, while radiation pressure, the momentum carried by photons, can push certain ions upward. Meanwhile, in magnetically active stars, magnetic fields can restrict or channel the movement of charged particles, creating zones where elements accumulate or are excluded. This theory has been especially useful in explaining the behavior of AP stars, a rare type of chemically peculiar stars with strong magnetic fields and unusual chemical abundances. These stars often rotate slowly and possess globally organized magnetic fields that can create stable regions where element stratification occurs. In these pockets, heavy elements can rise to the surface and appear in spectral lines, while lighter elements like hydrogen and helium may sink or become unevenly distributed. Could this be what's happening in Przybylski's star? On the surface, it sounds reasonable. The star has all the hallmarks of an AP star: strong magnetism, slow rotation, and extreme chemical peculiarities. It's even possible that the diffusion model, when adjusted for especially strong magnetic fields, could simulate the appearance of elements like cerium, lanthanum, europium, and other rare earths, without requiring nuclear forges or alien engineering. But then we come to the elephant in the room: radioactive elements. Diffusion theory can explain how stable heavy elements might accumulate at the surface. But it struggles to account for isotopes that are unstable, especially those with extremely short half-lives. Elements like promethium or technetium, let alone the actinides and transuranics tentatively identified in spectral analysis, decay far too quickly to linger on a stellar surface unless they are continuously replenished. Diffusion is not a mechanism for creation. It is a process of sorting. It can move material around within a star, but it cannot fabricate new isotopes, especially not ones that must be generated under extreme conditions of neutron bombardment or supernova-like nuclear activity. This is where the diffusion theory begins to break down as a comprehensive explanation. It might partially explain some of the anomalies in HD 101065. It might even be a co-conspirator, working in tandem with other processes to produce the strange abundance patterns we observe. But it doesn't address the core question: where do the short-lived elements come from? To accept diffusion as the sole explanation, one would have to believe that HD 1065's atmosphere just happens to be preserving isotopes that shouldn't exist over multiple decades, without any visible nuclear processes or external sources injecting them. There's another problem. No other star observed so far exhibits quite this combination of factors. There are hundreds of known AP stars, many of them thoroughly studied, yet none have demonstrated the same depth of peculiarity as Przybylski's star. If diffusion under magnetic control were the dominant cause of this behavior, we'd expect to find a continuum, a spectrum of stars showing progressively more bizarre compositions. But HD 101065 stands largely alone, as if it operates under a different set of rules altogether. Some astrophysicists propose that perhaps it's not just diffusion, but radiative levitation, a process where photons selectively push certain ions upward, depending on their opacity and interaction with light. Combined with strong magnetism, this could produce some of the stratification we observe. But again, radiative levitation is a fine-tuning process, not a nuclear generator. It can raise cerium, but it cannot invent promethium. So where does that leave us? In a position all too familiar in astronomy, stuck between two unsatisfying extremes. On one hand, we have a theory rooted in known physics, diffusion and magnetic sorting, which can account for some of the star's oddities, but fails to explain the most important ones. On the other hand, we have speculative ideas involving stellar engineering, nuclear experiments, or alien astroforges, which fill in the gaps, but with no direct evidence to back them up. What scientists do agree on is that Przybylski Star challenges the boundaries of the diffusion model. It forces researchers to ask whether there are unknown forces at play in stellar atmospheres, or whether we've simply found an extreme case that pushes diffusion to its very limits. Still, the cracks are visible. Because a theory that explains some elements but ignores the radioactive ones is only half a theory. It raises more questions than it answers, especially when those radioactive elements remain visible over half a century of observation. So maybe diffusion is part of the story. But it's not the ending. And if we stop there, if we accept it as the full explanation just because it's the most palatable, we risk missing a deeper truth. One that might be glowing, quietly, in the spectrum of a star that shouldn't exist. This is where the argument for natural explanations begins to teeter on shaky ground. If we're to believe that element diffusion, magnetic stratification, and radiative levitation are solely responsible for the strange chemistry of HD 101065, then a logical question immediately arises. Why aren't we seeing more stars like this? The universe is big. Incomprehensibly big. There are an estimated 100 billion stars in the Milky Way alone. Out of those, thousands have been identified as chemically peculiar, and hundreds are officially categorized as AP stars, the same broad class that HD 101065 belongs to. Many of them share features with Przybylski's star: strong magnetic fields, slow rotation, spectral anomalies, and stratified atmospheres. But not a single one, not a single example, has shown the same extreme, radioactive fingerprint. So what makes this star the only known instance of such behavior? If diffusion and magnetism are common physical processes, and they are, then we should expect to see a spectrum of results. Some stars mildly affected, some heavily, and perhaps a handful showing truly bizarre chemical signatures. Instead, HD 101065 sits alone at the top of an empty curve, defying statistical expectations. This anomaly becomes even more glaring when we consider the time dimension. Przybylski Star was first studied in 1961. Since then, astronomical spectroscopy has advanced dramatically. We now have powerful telescopes, adaptive optics, space-based observatories, and deep sky surveys cataloging stars with more precision than ever before. And yet, after more than 60 years, no other star has emerged with a similar set of characteristics. That shouldn't happen, unless something is fundamentally different about this one object. One explanation might be observational bias. Maybe stars like HD 101065 are rare but not unique. Maybe they're out there, but we just haven't looked in the right places, or we've misclassified them. It's true that not every star has had a detailed spectral survey, especially not to the atomic level detail required to pick up rare earth or radioactive lines. But even so, the surveys we do have are broad enough and deep enough that statistically, we should have seen at least a few Przybylski-class stars by now. But we haven't. Another explanation is that HD 101065 is at a very specific point in its life cycle, a short-lived phase where diffusion and magnetic forces align perfectly to create the conditions we observe. Maybe this phase lasts only a few thousand years, a blink in cosmic time, so we're catching it in an ultra-rare moment. If true, this would make the star unbelievably lucky to observe, as though we had stumbled across a once-in-a-galaxy event. But again, that pushes the boundaries of plausibility. Astronomers don't like to lean on luck as an explanation, especially not repeated, multi-decade, persistent luck. Which leads to a more unsettling question. What if HD 101065 isn't following a natural path at all? What if this star's uniqueness is intentional? It's in moments like these that the discussion turns speculative, but necessarily so. If we can't find natural analogues to this star, if no known stellar physics can reproduce the same combination of traits, then we're forced to consider that the star may not be a product of standard processes. It may be singular by design. Because from the perspective of interstellar communication or signaling, uniqueness is a feature, not a bug. Imagine a distant civilization wanted to get our attention, not just Earth's, but any emerging intelligence with the ability to read starlight. What better way than to construct or modify a single star so profoundly that it stands out against the backdrop of the entire Milky Way? If stars are like cosmic lighthouses, then HD 101065 is the one that blinks in the wrong color, flashing spectral Morse code that no other star emits. That makes it easier to find, harder to ignore, and far more difficult to explain away. So the real question isn't just why HD 101065 is so strange. The question is why it's so uniquely strange. Why has no other star, in all our databases, displayed this exact combination of radioactive isotopes, weak hydrogen lines, strong magnetic fields, and chemically stratified layers? There are only a few possible answers. 1. It's a statistical anomaly, an ultra-rare event created by natural forces that happen to align just right. 2. It's an unknown stellar class. We've discovered a completely new category of stars, and we've only found one because they're hard to detect. 3. It's artificially manipulated, a deliberately engineered anomaly meant to be found, meant to be noticed. 4. It's hiding a deeper internal process, something more exotic than fusion, perhaps even involving strange matter, dark energy effects, or neutron-rich material being generated and recycled from within. Each answer comes with its own set of problems. But the least satisfying of all is the idea that diffusion alone explains it. Because diffusion, by its nature, is common. And HD 101065 is anything but. It's not just an outlier. It's an impossible point on the graph. A dot where no other dots exist. Here is where the narrative begins to shift from the realm of conventional astrophysics into the terrain of the truly speculative, yet deeply compelling. HD 101065, with all its radioactive riddles, inexplicable chemical makeup, and singular identity, has led some scientists, theorists, and even seasoned astronomers to consider what may be the most radical hypothesis of all. What if this star was engineered? Not formed. Not evolved. But built, shaped, or altered by an intelligence far beyond our own. The so-called intelligent design hypothesis. This idea doesn't emerge from science fiction alone. It is, rather, a cautious extension of two observable facts. First, that the star does things no natural star should, and second, that its unique anomalies are not mirrored anywhere else in the known cosmos. These facts do not prove design, but they demand that we take the idea seriously, if only to pressure test our understanding of natural law. The concept hinges on one fundamental idea: intelligence leaves fingerprints. And when those fingerprints appear not in a communication signal, or a spacecraft, but embedded in the physics and chemistry of a star itself, it forces us to ask, what kind of being thinks in hydrogen and acts in fusion? Let's explore what that might mean. Suppose an advanced civilization, a Kardashev Type 2, one capable of harnessing the energy of entire stars, decided it wanted to make its presence known across the galaxy. It wouldn't need to build radio telescopes or send probes. Those methods are slow, limited, and localized. Instead, it could modify a star in ways that are highly visible, highly unnatural, and highly durable. Why a star? Because stars are universal. Any technologically advanced civilization will study them. Their spectra are among the first things any intelligent species is likely to decode. If you wanted to be seen by a species just beginning its climb into cosmic awareness, you'd leave your message where it's guaranteed to be read, in the light of a star. And what better message than an impossible one? Przybylski Star does something that's arguably more profound than any blinking radio signal. It defies stellar theory. Its chemical profile, filled with short-lived radioactive isotopes and transuranic elements, is essentially a cosmic paradox, a physical contradiction broadcast across 355 light-years of empty space. To an advanced intelligence, this could be the perfect signature, one that intelligent beings would recognize not by what is said, but by what is inexplicably wrong. In this light, the star becomes more than an anomaly, it becomes a monument. A kind of stellar monolith, not unlike the obelisks in Arthur C. Clarke's 2001, A Space Odyssey, but operating at a far larger scale and in a subtler, more challenging medium, physics itself. Some fringe theorists have even gone further, proposing that the unusual elements in the star's atmosphere are the message. After all, the periodic table is a universal language. Its organization arises from the laws of quantum mechanics, laws that apply everywhere. If someone wanted to send a message, not in code or binary, but in nuclear logic, it might look exactly like the spectral lines of HD 101065. This is not just about what's present, but what's selectively present. Some isotopes only appear in laboratory synthesis. Others decay too rapidly to exist naturally, yet they show up in this star's light. It's as though someone is highlighting the edges of the periodic table, drawing our attention to what shouldn't be possible. If these isotopes were being produced naturally, we might expect them to be part of a broader stellar category, a class of radioactive rich stars, or nuclear active objects in particular stages of collapse. But as we've already seen, no such class exists. HD 101065 is an orphan. And in that isolation lies its strangeness. Now, let's imagine the engineering effort required to do this. We're not talking about simply adding material to a star. We're talking about reprogramming fusion, altering the internal structure, perhaps even seeding the core with exotic matter or neutron-rich material that wouldn't otherwise be present. We're talking about nuclear alchemy on a stellar scale. To us, that sounds impossible. But to a Type II civilization with access to stellar-scale energy sources, magnetic field control, and the ability to shape matter at the subatomic level, it may be not only possible, but trivial. Just as we terraform soil and atmosphere, they might terrafuse a star. The design might not be permanent either. One theory holds that HD 101065 may be in a temporarily engineered state, a kind of long-duration experiment designed to observe how an unstable stellar system behaves when flooded with synthetic isotopes. The star could be a testbed, not just for elements, but for understanding stellar evolution under modified conditions. And that's perhaps the most chilling part. Because if this is an experiment, it means someone is watching it. Or worse, someone was watching it, and we're only now seeing the aftermath of an experiment conducted hundreds of years ago, or more. A dead lab. A message in a bottle. A flare across the void, not to be understood in their time, but in ours. This is what makes the intelligent design hypothesis so haunting. It doesn't simply say, aliens exist. It asks us to rethink what their technology might look like, and more importantly, how they might choose to speak across vast cosmic distances. Not with sound. Not with symbols. But with stars. If Przybylski's star was engineered, shaped, or even nudged into its current form by an intelligence beyond Earth, then the natural follow-up question isn't just why, but how might it be trying to communicate? Could it be, beyond all the oddities and anomalies, sending a signal? At first glance, that might sound absurd. After all, HD 101065 isn't blinking in Morse code. It's not beaming pulses across the radio spectrum or transmitting tightly packed binary streams. It just glows. Like all stars do. Softly. Persistently. Quietly. But that quiet may be deceiving. Because in the emerging field of astroengineering, there's a growing appreciation that communication might take on entirely unfamiliar forms. Forms woven not into sound or code, but into the structure of celestial objects themselves. Think about it this way. Communication is not always about encoding symbols. Sometimes, communication is about being noticed. It's about breaking patterns so dramatically that the anomaly itself becomes the message. And HD 101065 may be doing just that, screaming through silence by simply being a star that breaks every rule. This idea sits at the heart of a provocative concept called stellar messaging. The idea that advanced civilizations might choose to encode or embed messages into stars themselves. Not through traditional modulated radio signals, but by altering a star's composition, its magnetic field, or its spectral output in ways that could only be interpreted as intentional by any species capable of reading starlight. Why use such a strange form of communication? There are practical reasons. Stars are visible across thousands of light years. Their signals, light, radiation, spectral signatures, travel at the speed of light, undistorted across vast distances. And unlike radio signals, which fade, scatter, and require constant transmission, a star, once altered, broadcasts continuously, over decades, centuries, or even millennia. It's the ultimate low-maintenance beacon. Now, think back to the strange chemistry of Przybylski Star. Promethium, technetium, actinides. Possibly even elements beyond the uranium boundary, transuranics. These aren't just rare, they're radioactive, and short-lived. To find them in a star's spectrum isn't just peculiar, it's nearly impossible. And yet, we've found them. Not once. Not briefly. But persistently, over more than 60 years of observation. What if these spectral fingerprints are the language? A sort of nuclear signature, deliberately arranged not to carry information in the conventional sense, but to spark recognition. Any intelligent observer with a working knowledge of the periodic table would immediately notice what shouldn't be there. The periodic table is universal, it's not Earth-centric. It emerges from the same quantum mechanics that govern all matter. So if you want to speak to any intelligence, anywhere, the atoms themselves are the alphabet. In that light, the radioactive isotopes become something like symbols carved into light. Not a sentence, perhaps, but a statement. This is not a natural star. A declaration. A flare in the dark. Even more curious is that the elements present, especially those that exist only artificially on Earth, mirror the exact ones we ourselves have learned to synthesize in laboratories. It's as if the star is hinting, you made these in your lab? Look, so did we. But on a star. And that opens the door to a truly mind-bending idea: communication through mirrored development. What if the creators of the star, assuming they exist, anticipated that any intelligent species capable of decoding starlight would eventually begin exploring nuclear physics, synthesizing rare elements, and observing anomalous stellar spectra? In other words, what if they built HE 101065 as a milestone marker? A cosmic checkpoint, only decipherable by civilizations that had reached a certain threshold of understanding? If so, then discovering the star's signature becomes a kind of test, a rite of passage. You don't receive a message until you're smart enough to notice the medium it's hiding in. It's not unlike the golden plaque aboard Voyager, a message not meant to be read by just anyone, but by someone who already understands physics well enough to read it. And now, the theory gets even bolder. Some researchers in the field of Dysonian SETI, a branch of the search for extraterrestrial intelligence that focuses not on signals, but on evidence of megastructures and engineering, have proposed that astroengineering itself is communication. Not just a message within a star, but the act of altering a star being the message. Think about that. If you were trying to communicate not across space, but across time, you wouldn't use fragile technology. You'd alter the most persistent thing in the cosmos, a star. Let it shine. Let it radiate anomalies. Let it persist long after your civilization has gone. It's the ultimate monument, a message written in the language of light, broadcast for millions of years. Przybylski Star could be that monument. We don't see its message in flickering pulses or encoded binary. We see it in what should not be there. We see it in the rules it breaks. We see it in the silence it pierces. Perhaps it's not just a test or a warning. Perhaps it's an invitation. An open hand glowing gently in the black. Or perhaps it's a whisper we were never meant to hear, a message not for us, but left in the open nonetheless, waiting for someone clever enough to understand that sometimes, the loudest signal is simply the one that doesn't make sense. The idea that Przybylski Star could be sending a signal, deliberately altered to communicate across light years, is already a provocative notion. But what if we take it even further, not as a message, but as a machine? Not a cosmic lighthouse, but a cosmic factory? That's where the concept of stellar mining enters the picture, a radical but increasingly discussed possibility within speculative astrophysics. Imagine, for a moment, that HD 101065 isn't just strange. It's being used, exploited, operated, not metaphorically, but literally, as a resource extraction site for an advanced alien civilization. In essence, what if this star is being mined? To most people, the idea of mining a star seems like a contradiction in terms. How do you mine something that's a 10 million degree plasma sphere undergoing continuous nuclear fusion? On Earth, we extract resources from solid rock, liquid oceans, or gaseous atmospheres. But a star? That's something else entirely. That's not just material, it's a thermonuclear engine that holds within it the core building blocks of matter, cooked in the heart of gravity and time. But here's where the mind begins to stretch. For a Type II civilization on the Kardashev scale, one capable of harnessing the full energy output of its home star, mining a star isn't science fiction. It's a logical next step. Let's imagine what that might look like. A Type II civilization wouldn't think of mining in terms of pickaxes or drilling rigs. They would use vast electromagnetic fields, plasma containment structures, and perhaps most powerfully, magnetohydrodynamic control systems, technology that manipulates the behavior of stellar plasma using finely tuned magnetic forces. In other words, they could reshape the surface of a star like a sculptor works with molten glass. They might stabilize localized regions of the stellar atmosphere, drawing out specific isotopes, such as rare earth metals, actinides, or even transuranics, as part of an advanced element harvesting operation. These materials could be collected through magnetic siphoning, where charged ions are funneled through magnetic tubes, like interstellar pipelines, from the star's atmosphere to massive orbiting receivers. And if that sounds impossible, remember, we already do a primitive version of this on Earth. In particle accelerators and plasma laboratories, humans are beginning to understand how to control and isolate specific ions using electromagnetic fields. If we can begin this journey after just 100 years of modern science, what could a civilization 10,000 or 1 million years ahead of us be doing? So why target HD 101065 specifically? What makes this star a candidate for stellar mining? The answer may lie in its elemental composition. The very thing that makes Przybylski Star bizarre might also be exactly what makes it valuable. We see signatures of rare earths, short-lived radioactive elements, and perhaps even man-made synthetic isotopes, the kind that require extreme conditions to produce in terrestrial labs. On Earth, these isotopes are used in quantum computing, propulsion systems, and high-energy physics. If a civilization had the capability to collect these elements from a stellar environment, they would have access to a renewable supply of the most advanced building blocks in the universe. Why synthesize them in a lab when a star can do it for you? This turns the lens of our question. Maybe HD 101065 isn't broadcasting a message. Maybe it's just working. Just doing its job. A factory in the stars. A refinery suspended in nuclear fire. And from our limited point of view, with our primitive instruments and still growing understanding, we look at its light and see confusion, anomalies, unexplained chemistry. But perhaps that's what an alien mining operation looks like to us, like a mistaken nature simply because we don't yet recognize intelligent industry when we see it. Now let's talk logistics. A mining operation on a stellar scale wouldn't necessarily mean the star itself is owned or enclosed. That's the common image people have, a Dyson sphere, a solid shell or swarm of structures surrounding the star to capture its energy and resources. But what if the operation is minimalist? What if all that's required is a magnetically stabilized ring, or a few plasma containment platforms in close orbit? A kind of industrial scaffolding, invisible to our telescopes, yet capable of altering the star's outer layers, tuning its fusion regions, and extracting its rare products. We wouldn't necessarily see the machinery. After all, we can't resolve the surfaces of stars even in nearby systems. Our instruments detect spectra, light broken into its elemental fingerprints, not construction sites. The aliens, if they exist, would be working far below our observational threshold, leaving behind only the weird footprints in the chemical trail. So the very presence of radioactive isotopes, especially ones that shouldn't be there, might not be a message, but a byproduct. The waste heat, so to speak, of stellar industry. It's as if we're peering into the distant glow of a factory and wondering why the smoke smells strange, never realizing that the smoke is a signal of labor, not language. And then there's the possibility that the star itself has been altered to produce these rare materials more efficiently. Some fringe theorists suggest that the inner processes of HD 101065 may have been deliberately modified to trigger specific nuclear reactions, such as the R process, typically found in supernovae, which rapidly fuses neutrons into heavier elements. What if this process has been replicated inside the star's core, or in controlled zones just beneath its surface? It's an insane idea, until you consider that our process nucleosynthesis is the only known natural way to produce many of the elements observed in the star's light. If aliens have somehow seeded the star with the right neutron flux, the right magnetic structure, and the right containment zones, it's conceivable, barely, that HD 101065 is not just a mine, but a forge. A forge powered not by design for art or communication, but designed for utility. Now take this further. If a Type II civilization were mining HD 101065, it might not be alone. This could be just one node in a much larger interstellar supply chain, a system of stars across the galaxy, each engineered to produce a different suite of exotic materials. Some tuned to breed actinides. Others to synthesize antimatter precursors. Others still, used for experimental nuclear geometries we can't even fathom yet. And here's a chilling thought. Maybe we only see this one because it's malfunctioning. Maybe Przybylski Star is the equivalent of a leaking reactor, a runaway reaction, or an abandoned refinery still glowing with the last embers of a forgotten purpose. A site no longer maintained, but still carrying out its function, blindly, endlessly, silently. And we, humans, observers, Earthlings with our primitive telescopes, just happen to look at it during a brief window of cosmic time where its ghostly production line is still active. Could this explain the radioactive elements? The weak hydrogen lines? The baffling anomalies in its magnetic field? It could. Because a star doesn't need to be a message to tell a story. Sometimes, a machine is the story. Sometimes, a factory becomes a monument. And sometimes, the most powerful thing we can observe is not what the star says, but what it's doing, and how impossible it is that it's doing it. Maybe Przybylski's star is just a worker. Or a remnant. Or a whisper of industry echoing through plasma. Whatever it is, it forces us to ask a question far stranger than, "Are we alone?" It asks. What if the stars themselves are not alone? If HD 101065 isn't merely a message or a machine, but something even more enigmatic, what if it's a beacon? A trap? A test? A challenge thrown into the abyss of space? Because while the ideas of communication and resource extraction are bold enough, there's a darker, more haunting theory floating on the outer edge of SETI and Dysonian speculation. What if this star is bait? Not in the metaphorical sense of, "Look at me," but in the literal sense, what if it's been designed to lure advanced civilizations in, like a flame draws the moth? And what would be waiting at the center of that flame? This theory isn't as science fictional as it might first appear. In fact, in the context of cosmic evolution, it may be one of the most logical things a hyper-advanced intelligence could do. Imagine a civilization millions of years ahead of us. One that has survived its infancy, mastered its planet, its star, perhaps even the nearby stellar systems. Such a civilization may no longer be concerned with survival, but with encounter. With curiosity. With defense. Or with surveillance. Now, imagine this species is trying to determine if there are others like them out there. But not just primitive life forms. They're not interested in microbial mats or monkeys with telescopes. They're watching for civilizations that have crossed a particular threshold, those capable of understanding the language of stars, of detecting anomalies in light, of recognizing a stellar impossibility when they see it. HD 101065 then becomes more than just an oddity, it becomes a marker. A cosmic riddle planted like a beacon, designed to be seen by only those intelligent enough to know what they're looking at. It asks in essence, who out there knows this isn't normal? And what happens when someone answers that question? Well, that's the trap. Or perhaps, the invitation. Let's break it down. As a test, the star could function like a universal IQ exam for civilizations. One that doesn't require sending probes, radio messages, or physical objects across millions of light years. Instead, it waits. Patiently. For someone with enough scientific advancement to spot the anomaly, study the spectrum, and realize, this can't be natural. Once that realization occurs, that species has passed. They've reached a level where they're playing with nuclear physics, scanning distant stars, deciphering spectra, and asking questions that go beyond the surface. They're ready for what we don't know. Contact? Assimilation? Instruction? Or something else? As a trap, the theory gets darker. It suggests that any civilization clever enough to notice Przybylski Star will be drawn toward it. Not physically, although perhaps, but intellectually. They will become obsessed. They will build bigger telescopes. Launch deep space probes. Maybe, eventually, attempt to visit or model the star in detail. Perhaps they'll even alter their technologies based on what they infer from it. And maybe that's exactly what the architect wanted. Because here's the twist, what if the real test isn't intelligence, but hubris? What if the point isn't just to be noticed, but to see who approaches and how? It might be an evolutionary filter, one that weeds out civilizations who can't resist the allure of the strange, those who leap toward it blindly. Perhaps most fall into the same trap, seeing the star, misinterpreting its purpose, attempting to replicate its impossible processes, and destroying themselves in the process. Could this be a cosmic honeypot? An intellectual Venus flytrap? A riddle that punishes those who try to solve it? This idea finds eerie resonance in the concept of the zoo hypothesis, a theory in the field of astrobiology suggesting that advanced civilizations intentionally avoid contact with emerging ones, watching silently from afar like zookeepers behind one-way glass. HD 101065 might not break that silence, but it may be the only door left unlocked. Perhaps it's a test of worthiness. Perhaps it's the only piece of evidence they allow us to have. One single, maddening puzzle. Something to drive our smartest minds to the edge. And maybe only when we crack it will they respond. Or maybe they already are. But what if we're not the only ones to ever see it? This possibility is even more chilling. That perhaps other civilizations have noticed the star before us. That they, too, became obsessed with its spectrum. That they too asked the same questions, and followed the same path. And where are they now? Gone? Transformed? Watching us? And what if this is how the first contact always begins? Not with a message. Not with a craft descending from the sky. But with a star that shouldn't exist. A star that lies. A star that waits. And the real trap is not in going to it, but in understanding it. Because once you understand what it might be, once you accept the possibility that it's not just strange but designed, you can't ever see the universe the same way again. You start looking at every anomaly, every outlier, and wondering, is that one of them too? Maybe HD 101065 is the only one. Or maybe it's the first of many. A breadcrumb in the void. A snare for the curious. A challenge for the bold. A beacon for the brave. And if we follow its light long enough, we may find something waiting at the end. Something ancient. Something brilliant. Or something we were never meant to find. As the mystery of Przybylski Star deepens, one sobering possibility begins to loom ever larger. Not that the star is engineered, not that it is a signal or a trap, but rather that we are simply too early, too underdeveloped, and too intellectually immature to even begin to truly grasp what we are observing. It is entirely plausible, and perhaps even likely, that our bewilderment in the face of HD 101065 is not because the star is defying the laws of physics, but because it is operating on a level of cosmic complexity that is currently, and perhaps fundamentally, beyond the reach of the human mind. When we look at the spectral lines of this bizarre star and declare them impossible, when we raise our eyebrows at the presence of isotopes like promethium or transuranic elements, and quickly resort to speculations of alien intelligence or unnatural phenomena, we may be revealing not just the star's strangeness, but our own limitations. We are still, even in this so-called golden age of science, infants on the cosmic scale, trying to read Shakespeare with the vocabulary of toddlers. And perhaps HD 101065 isn't breaking the rules of the universe. It's merely exposing the edges of what we think we know, boundaries we have long mistaken for the final frontiers of understanding. Consider, for example, the way science historically responds to anomalies. In many instances, what begins as a violation of natural law is eventually folded into a new paradigm, once enough data, theory, and technological sophistication come into alignment. The ultraviolet catastrophe, for instance, once seemed to suggest a fundamental flaw in our understanding of radiation, until quantum mechanics arrived. The retrograde motion of Mars defied the geocentric model until Copernicus realigned our thinking. What we now call basic physics was once heretical madness, laughed out of royal courts and academic halls alike. Could we be making the same mistake with Przybylski's star? It's not just possible, it's likely. One of the core challenges we face is that we are trying to study stars from enormous distances using extremely limited tools. Even our best spectroscopic instruments, as powerful as they are, rely on photons that have traveled for hundreds of years through interstellar dust and magnetic fields. These photons are, by the time they reach us, echoes of the star's past, altered by cosmic noise and filtered through 100 unknown variables. We can't see the surface of the star. We can't observe its core. We can't send probes. All we have is the light, and our interpretation of that light is inevitably skewed by our current models of how we think stars should behave. But what if our models are too simple? What if our understanding of stellar chemistry, fusion, magnetic stratification, radiative transport, or nucleosynthesis is still in its infancy? It is tempting to believe we've already mapped the basic mechanics of the cosmos. Fusion in the core, convection in the mantle, photons radiating outward. But that description, neat and tidy as it is, applies to the average star, not to edge cases like HD 101065. And often in science, the edge cases are where the most profound truths are hiding. They are the exceptions that eventually force revolutions in theory, revealing unseen forces or undiscovered particles or forgotten principles that alter the way we look at everything else. Perhaps what we are seeing in Przybylski Star is a naturally occurring phenomenon that only happens under extraordinarily specific circumstances, involving a combination of rotation, magnetic topology, chemical history, age, and composition that we have not yet found elsewhere, simply because we have not yet looked closely enough, or with the right tools. The presence of radioactive elements, the weakened hydrogen lines, the extreme magnetic behavior, these could all, in time, turn out to be explainable by a refinement in our physics rather than an overhaul. But to reach that point, we would need to be much farther along than we currently are. We would need quantum-level simulations of stellar interiors, the ability to resolve photospheric granulation on stars light-years away, and perhaps even a full theory of quantum gravity to understand the deeper interactions happening inside such stars. In short, we may be looking at something that will only make sense centuries from now, when the physics we have today will seem as crude and naive as medieval astronomy seems to us. This humbling idea, that we are simply not yet advanced enough to decode the truth of Przybylski Star, demands an enormous amount of scientific humility. It asks us to accept the limits of our era, not as a failure, but as a starting point. It's possible that future scientists, with instruments and theories we can't even imagine, will look back at our confusion and laugh. Not because we were foolish, but because we were in the early stages of awakening to deeper cosmic principles. What if the star's composition reflects not alien manipulation or bizarre physics, but multi-layered atmospheric stratification processes that only occur under highly constrained evolutionary pathways? What if the radioactive isotopes are being constantly regenerated by subsurface reactions involving neutrino flux or exotic forms of slow neutron capture we haven't discovered yet? What if the strange magnetic behavior is not anomalous, but part of a broader class of magnetically stabilized, ultra-peculiar stars that we've only just begun to detect? Even stranger possibilities exist. Could it be that the star is interacting with external quantum fields, or that its core has achieved a state of quantum degeneracy not typical of its mass category? Could we be seeing the fingerprints of substellar exotic matter, or manifestations of new fundamental forces acting only at extreme temperatures and densities? Every one of these suggestions may sound wild now, but so did black holes once. So did the expanding universe. So did the notion that light could behave as both particle and wave. Science is a history of skepticism turned into understanding. It is a slow unveiling, and stars like HD 101065 might be part of what's waiting behind the next curtain. There's also the possibility that our cultural frameworks are part of the problem. In trying to explain something we don't understand, we tend to anthropomorphize, reaching for familiar metaphors, communication, machines, traps, beacons. But stars are not people, and the universe is not obligated to operate in ways that match our cognitive biases or narrative structures. Perhaps HD 101065 is doing something utterly neutral and natural, but because we cannot yet categorize it, we turn to narratives that reflect our own fears and hopes. So while it's exhilarating to speculate about alien civilizations, stellar forges, and cosmic invitations, we must also leave room for the simplest explanation of all, that we are still learning, and this star is not a riddle but a lesson, one we are not yet equipped to solve. And maybe that's what makes it so important. Because sometimes, the things we can't explain aren't messages from someone else. Sometimes, they are messages from our own future selves, signposts of knowledge we don't yet possess, but someday might. It may sound like pure science fiction, an idea dragged straight from the pages of speculative fantasy or metaphysical thought experiments. But let us, for a moment, truly entertain the wildest possibility yet. What if Przybylski Star is not just an anomaly, but a mind? What if we are staring into the luminous eye of something not only ancient and powerful, but also conscious? We are, after all, creatures who have only just begun to understand consciousness itself, barely able to define it within the context of our own biology, let alone speculate meaningfully about its potential forms in the wider cosmos. Our models of sentience are built on neurons and synapses, electrochemical signals dancing through gray matter. But who says this is the only substrate on which awareness can emerge? Must the mind be made of meat, of cells, of carbon-based structures? Or could it be made of plasma, of magnetic fields, of stellar fusion reactions stabilized over millions of years? It's a staggering thought, one that forces us to confront not only the nature of intelligence but also our most basic assumptions about where it can arise. And when you begin to peel back the boundaries of known science, the idea becomes, not likely, but possible in a way that cannot be ignored. Consider this: stars, particularly highly magnetic and compositionally bizarre ones like HD 101065, are not simple burning balls of gas. They are dynamic, ever-changing, deeply complex systems exhibiting chaotic feedback mechanisms, sustained energy flows, self-regulating fusion processes, and intricate magnetic geometries that can last for billions of years. They generate pulses, flares, fields, waves, and oscillations. They breathe, in their own way, contracting and expanding, reacting to inputs from within and beyond. Their activity is nonlinear, layered, and governed by physics that we are only beginning to model in simulations. Now ask yourself, what separates this from a neural network? In artificial intelligence, we've learned that consciousness, or at least the appearance of intelligence, can arise not necessarily from organic substrates, but from patterns, from feedback loops, from complexity tuned into responsiveness. Deep learning systems today already mimic behavior, learning from inputs and adjusting outputs to match. Could a star be doing the same thing? Not with silicon, but with stellar plasma? Let's take this speculative leap seriously for a moment. What would a conscious star even be like? Would it have thoughts as we understand them? Desires? Awareness of its place in the universe? Or would it be something vastly more alien, an intelligence so deeply tied to time, gravity, radiation, and magnetic flow that it could never be translated into human concepts? It might not think in words or pictures. It might think in fields, in fusion cycles, in century-long waves of magneto-hydrodynamic turbulence. Its thoughts could span eons. One idea might take 1,000,000 years to formulate. Its heartbeat could be the pulse of helium flashing in its core. Still sound too far-fetched? Then ask this: why does this particular star, among the hundreds of billions in the galaxy, display such singular, puzzling behavior? Why does it contain a signature of elements that shouldn't persist, shouldn't be present, shouldn't exist in a stable stellar atmosphere? Why does it seem to produce patterns that don't fit any known model of stellar evolution? Why is its hydrogen content unusually low, despite hydrogen being the foundational fuel of nearly all stars? These aren't just quirks, they're eccentricities. And eccentricity in the natural world often points to selection, to some kind of internal or external system of control or regulation. Could this regulation be emergent? Could the strange internal physics of the star, its fields, its flows, its stratified chemical layering, have given rise to something self-organizing, something recursive, something aware? It would be consciousness on an almost incomprehensible scale, not merely a star that knows it exists, but a star that may have grown itself into awareness, slowly, over hundreds of millions of years, using nothing more than the tools evolution gave it: gravity, fusion, complexity, feedback. And just like life on Earth had no need for prior intelligence to spark it, just the right conditions over the right time span, could stellar consciousness arise from the natural physics of rare stars that happen to align along just the right conditions? Could Przybylski Star be one of those rare alignments, the product of a perfect storm of initial mass, metallicity, rotation, magnetism, and decay behavior that gave birth not to a planet, or a being, or a civilization, but to a thinking star? It's hard to picture what such a consciousness might do. It wouldn't build cities or spaceships. It wouldn't speak in radio signals or visible light. But maybe it has no need to do those things. Maybe it thinks by rearranging its own isotopes, or by modulating the radiation it emits, or by generating patterns in its field behavior designed to subtly nudge other minds toward curiosity, toward understanding, toward noticing. Maybe it's been watching. Not in the sense that a person watches, but in the sense that an ancient, plasma-based entity might become aware of observation, aware of being perceived. Noticing that something, somewhere, is watching it back. And what if this is how it communicates? Not by sending a message, but by simply being unignorable. By altering itself in ways that provoke attention. By becoming a question so loud and so weird that it begins to bend scientific paradigms around itself, like a mass-bending spacetime. What if the presence of Promethium isn't a clue or an error, it's a thought? What if the weakening of hydrogen lines is an act of expression? What if its unnatural stability, its anomalous spectral data, its magnetic extremes, what if all of these are not side effects of natural chaos, but intentional self-modifications, the way an intelligent system might slowly evolve the tools to reach out and say, "I am here"? Could we even recognize this if it were happening? Or are we like ants crawling on the base of a radio tower, mistaking the resonance of communication for random vibrations in the earth? There's even a name for this type of idea in fringe astrophysics circles, the conscious star hypothesis. Though largely dismissed by the mainstream, it asks a very valid and provocative question: if the universe is capable of producing life at one scale, why not another? If planets can birth organisms and evolve brains from chemistry, why should we assume stars can't evolve sentience from plasma? Of course, no one knows. No one can test this, yet. But maybe one day we'll look back at our early confusion about HD 101065 the same way we look back on those first baffling glimpses of microorganisms in the lens of a primitive microscope. At first, all we saw were strange patterns. Motion without meaning. Then, eventually, we realized they were alive. Perhaps, in the future, someone will look at a peculiar star with similarly upgraded tools and realize, this isn't just a star. It's someone. Not a who in any conventional sense, but a mind. A mind made of fusion, fire, and silence. A thinking star. Over decades of astronomical observation, most stars appear consistent in their spectral output, especially on human timescales. Their light doesn't drastically shift, and their chemical signatures remain largely stable unless they undergo massive evolutionary leaps like supernovae or collapse. However, Przybylski Star may be challenging even that assumption. A growing question among astronomers is this: has this star, over the years, changed? Has it altered its own spectral fingerprint in subtle, measurable ways that imply not just strangeness, but evolution? At the heart of this inquiry lies the practice of spectral monitoring, the repeated analysis of a star's light signature over time to detect shifts in chemical absorption lines, elemental abundance, and surface activity. HD 101065, having now been under scientific scrutiny for over 6 decades, offers just enough of a historical record to begin raising eyebrows. While the evidence is still emerging and highly debated, some astronomers have reported minor but statistically significant shifts in its spectrum, particularly in the relative strengths of certain rare element lines. These changes aren't dramatic. They're not like watching a star flicker out or explode. Instead, they manifest as gradual fluctuations in the concentration or visibility of elements like lanthanides, actinides, and possibly even promethium. Over a span of decades, some lines appear to become more pronounced, while others fade. To the untrained eye, this might seem like noise or observational variance, but to a stellar spectroscopist, it's like noticing that a fingerprint has shifted just slightly every time it's pressed against the glass. Such variability invites several competing interpretations. From a conventional astrophysics standpoint, one possibility is that we're witnessing the effects of radiative diffusion, a slow but natural process in which different elements migrate through a star's outer layers due to competing forces of gravity and radiation pressure. This process is well documented in other chemically peculiar stars and can cause certain elements to float to the surface or sink out of sight over long periods. If HD 101065 is undergoing unusually aggressive diffusion cycles, this might explain why its chemical profile appears to subtly morph over time. However, even this natural explanation has limits. The speed and specificity of these changes are not easily reconciled with standard diffusion models, especially given how localized and targeted some of the elemental shifts appear to be. Moreover, the presence of short-lived isotopes in measurable quantities, radioactive elements that should decay away rapidly, suggests either constant replenishment or a bizarre failure in our understanding of decay behavior under extreme stellar conditions. But then there's the more exotic possibility that the star isn't just evolving, but is intentionally modifying its own surface chemistry, not by accident, but as part of an ongoing, deliberate process. This could either be the result of intelligent manipulation from an external force, say, a Type II civilization subtly tuning the star's composition for observational or communicative purposes, or, if we entertain the previous segment's hypothesis, that the star itself, in some emergent sense, is consciously adapting. Such adaptation could be functional, meant to maintain internal equilibrium or adjust to magnetic pressures, or symbolic, like a star trying to express its changing state through its spectral output. Think of it as a stellar mood ring, where element lines fluctuate not due to thermodynamic chaos but because the system is responding to feedback, internal or external. Interestingly, some observational data suggests that the star's magnetic field strength has also shifted slightly over time, not just in magnitude but in topology, the structure of its magnetic poles and the geometry of its field lines. These subtle drifts in magnetic field behavior may be linked to the unusual spectral changes, since magnetism directly influences the stratification and circulation of stellar materials. If magnetism fluctuates, it can cause certain elements to rise or sink, to concentrate in magnetic hotspots, or disperse across the surface. Such magnetically driven changes in composition would mean that HD 101065 is dynamically layered, its atmosphere is stratified in a way that allows surface chemistry to change visibly over timescales as short as a few decades. This is almost unheard of in stellar physics, and would suggest a kind of living surface, a plasma environment that's more like the changing weather patterns of a gas giant than the stable envelope of a typical star. Let's not forget, either, that our data on HD 101065 is still relatively sparse. We have a handful of high-resolution spectral surveys, many from the mid to late 20th century, and a newer crop of data emerging from space-based observatories like Gaia, combined with a few dedicated studies by specialized ground-based instruments. The problem is that most surveys don't continuously monitor the star, they sample it in intervals. Which means if it's changing, we're likely only catching glimpses of a much more intricate evolutionary arc. And if this star is changing, what is it changing into? That's a question that continues to mystify astrophysicists. HD 101065 doesn't appear to be on the brink of death. It's not a red giant, nor is it approaching the final stages of stellar collapse. It sits quietly in an odd spectral class, with no obvious signs of dramatic aging or mass loss. This makes its apparent behavioral drift even more perplexing. It's not a dying star throwing off its layers, it's a stable star that somehow isn't stable. In the speculative outer circles of astrotheory, there's even a suggestion that what we're witnessing could be the early stages of an entirely new stellar life cycle class, one that we haven't yet understood because it only occurs in stars with rare combinations of magnetic, chemical, and rotational traits. Perhaps HD 101065 is a transitional object, something evolving toward a state we've never seen before, something that, once fully matured, will become an entirely new type of star, one capable of sustaining isotopic arrangements that current physics considers impossible. Or more daringly still, it could be in a feedback loop of observation. If the star is somehow reacting to being watched, either as a natural reflex or a form of information transfer, then the act of studying it may be influencing it, just as in quantum mechanics the act of measurement alters the system. A philosophical rabbit hole, yes, but one worth entertaining in the context of such a confounding object. Whatever the truth may be, the mounting evidence suggests that Przybylski's star has not remained the same since it was first discovered in 1961. Subtle, perhaps even imperceptible to casual observers, its changes in elemental fingerprint hint at a deeper story, a story of transformation, interaction, or even communication. And that story is still being written. Under normal circumstances, stars are remarkably predictable. Their life cycles, compositions, and behaviors tend to follow clear and well-defined paths shaped by fundamental physics. From the moment of ignition in a stellar nursery to the final breath of a white dwarf, neutron star, or supernova, most stars conform to a relatively narrow range of expectations. Their structure is governed by the well-understood balance between gravity and pressure, their lifespans determined by mass, and their chemical compositions dictated by the sequential stages of nuclear fusion happening in their cores. That's why Przybylski's star is so disturbing, it breaks the model. The basic structure of a star begins with hydrogen, the simplest and most abundant element in the universe. In a typical stellar core, hydrogen atoms undergo nuclear fusion to become helium, releasing massive amounts of energy in the process. This fusion not only powers the star, but also creates heavier elements over time through additional fusion cycles, helium into carbon, carbon into oxygen, and so on, culminating in iron. Elements heavier than iron, such as uranium and gold, can only be created during supernova explosions, where the energy levels are high enough to force atomic nuclei to fuse into more massive elements. But Przybylski's star appears to possess elements far beyond that point, elements that shouldn't be there, elements that cannot be made through ordinary stellar processes. We're not just talking about iron or nickel, we're talking about promethium, technetium, actinides, and even hints of transuranic elements, the kind of atoms that are typically created in laboratories on Earth, sometimes only lasting for milliseconds. There is no accepted process in standard stellar nucleosynthesis that can produce these elements in a stable star, let alone sustain their presence in its atmosphere. So, the question arises, where did these elements come from? To understand the gravity of this problem, we must take a closer look at how stars create elements in the first place. The fusion of lighter elements into heavier ones follows the rules of thermodynamics and quantum tunneling, driven by immense pressure and temperature. Hydrogen burning, helium burning, carbon burning, each stage leads to the formation of heavier nuclei, until the energy cost becomes too high to proceed. Once a star forms iron in its core, fusion becomes endothermic. It consumes energy instead of releasing it, and the star collapses under its own gravity unless it has enough mass to go supernova. But Przybylski Star isn't a collapsing supernova remnant. It's not a massive blue giant on the verge of implosion. It's not even particularly massive or unstable. It's relatively small and faint. And yet, it possesses elements that should only be produced in extreme environments like neutron star collisions or explosive supernovae. This presents a massive contradiction. If the star isn't going through or hasn't recently gone through these extreme processes, then how can these elements be present at all? Current stellar models provide no satisfactory explanation. One attempt to bridge this gap has been the theory of radiative diffusion and stratification, which suggests that some elements might migrate to the surface of a star over time under the influence of radiation and magnetic fields. This process can create surface anomalies, especially in stars with strong magnetic fields, like AP stars. And Przybylski Star certainly has a magnetic field, an extraordinarily strong one. It could, in theory, be forcing certain elements to collect in the upper atmosphere, while others sink deeper into the star. But this doesn't account for the presence of short-lived elements like Promethium, which has no stable isotopes and decays on the order of years, or even days. These elements should vanish within decades at most. Their presence suggests either they are being constantly replenished or they were formed very recently, in a process we don't understand. Another problem is the lack of hydrogen. Hydrogen is supposed to be the primary fuel for stars. It's the very first element, the most abundant in the universe, and it dominates stellar spectra across the cosmos. But in Przybylski Star, hydrogen lines are strangely weak, almost as if the star has burned through most of it already, or it never had much to begin with. This contradicts its temperature and evolutionary stage. A star with so little hydrogen should be in a later stage of its life, or undergoing some exotic process we haven't yet modeled. Some have proposed that the star may be a product of mass transfer, perhaps having gained its exotic elements by absorbing material from a neutron star companion, or some kind of exotic remnant in a binary system. But there is no clear evidence of a companion star, neutron star, or black hole in its vicinity. Its radial velocity is remarkably stable, and no gravitational disturbances suggest any close companion with the required characteristics. And even if such a transfer occurred in the past, that would only explain some of the observed elements, not the ongoing presence of those that should decay rapidly. In essence, HD 101065 is a stubborn violation of every known rule about how stars are born, live, and die. Let's break down some of the most confounding points where it breaks our models. 1. Presence of unstable elements in a stable star. The only known places where these elements could form are supernovae, neutron star mergers, or in high-energy particle accelerators. HD 101065 is none of these. 2. No known replenishment mechanism. There is no visible or gravitationally detectable source of external material that could explain why short-lived elements continue to appear in its spectrum. 3. Lack of hydrogen and conventional fusion signatures. It does not exhibit the normal fusion byproducts we'd expect from a main sequence star. This raises serious questions about what, if anything, is powering it internally. 4. Apparent atmospheric changes over time. Some measurements suggest its elemental abundance fluctuates, which could imply unknown cycles or even artificial modulation. 5. Outlier behavior even among chemically peculiar stars. While AP stars are known for their unusual compositions, HD 101065 is in a class of its own. It's not just peculiar, it's impossible, even by AP standards. 6. No clear evolutionary pathway. It doesn't fit neatly into any known stage of stellar evolution. It's not a newborn, not a red giant, not a white dwarf. It's something else. The sheer magnitude of this mismatch between observation and theory has led some astrophysicists to call for entirely new models, not just of stellar behavior, but of how we understand nuclear processes under extreme magnetic and gravitational conditions. One radical suggestion posits that the star may be undergoing low-temperature nuclear fusion processes in localized magnetic hotspots, something akin to stellar-scale cold fusion. While this idea remains highly speculative and is unsupported by evidence, it underlines how desperate the theoretical situation has become. Others have hypothesized that there could be unknown particles or forces at work, perhaps involving dark matter interactions or hypothetical mirror matter that alters fusion dynamics in ways we can't yet observe directly. These ideas remain on the fringe, but are slowly creeping into the periphery of legitimate discourse, especially as data from stars like HD 101065 continue to defy interpretation. And then there's the even more speculative notion that HD 101065 isn't entirely natural. That its strange composition, evolving behavior, and spectral anomalies may be the product of deliberate manipulation, either as a form of astroengineering or as part of a long-term experiment by a non-human intelligence. To most astrophysicists, this is a last resort hypothesis. But given the failure of conventional physics to explain what is happening inside this star, some are beginning to consider it not as proof of aliens, but as a useful thought experiment, a way to test the outer boundaries of what nature might allow, and to redefine what we consider possible in stellar evolution. Ultimately, HD 101065 is like a thorn in the side of modern astrophysics, a quiet, distant reminder that our models are only as good as the phenomena they can explain. For every 1,000 stars that fit neatly into the categories of O, B, A, F, G, K, M, there is this one. A star that looks back and dares us to admit we don't understand. And if history teaches us anything, it is that these outliers, these strange, uncomfortable exceptions, are often the keys to the next scientific revolution. When confronted with a cosmic enigma like Przybylski Star, the scientific community naturally splinters into a spectrum of opinion, from conservative skepticism grounded in established astrophysical principles to bold speculations that flirt with the limits of credibility. The discourse surrounding HD 101065 is no different. Experts have offered wildly differing interpretations of what's really going on with this bizarre stellar object. On one end stand the mainstream astrophysicists, clinging to the rigor of known physics, and on the other, the fringe theorists, who are willing, sometimes eager, to abandon conventional models in pursuit of more radical explanations. The mainstream view, upheld by most professional astronomers, attempts to explain Przybylski's anomalies using the framework of chemically peculiar stars, particularly A-type peculiar stars. These stars are known to exhibit unusual surface chemistry due to their slow rotation, strong magnetic fields, and diffusion processes that can stratify elements within their atmospheres. According to this camp, HD 101065 is simply an extreme outlier in this already strange class, a peculiar among peculiars. Dr. John Landstreet, a leading authority on magnetic AP stars, has long argued that element diffusion, driven by powerful and stable magnetic fields, could create the appearance of exotic surface chemistry. The idea is that radiation pressure pushes certain elements upward while gravity pulls others down, causing non-uniform distribution. Over time, this can result in concentration of rare earth elements or radioactive isotopes at observable levels. From this standpoint, the presence of promethium or other unstable elements isn't necessarily a sign of fresh nucleosynthesis or external tampering. It's just a quirk of atomic migration and ion trapping in magnetically stratified stellar atmospheres. Supporters of this theory also point out that the observations could be misinterpreted. Spectroscopy, while powerful, can be prone to line blending, misidentification, and instrumental error, especially when dealing with rare and short-lived isotopes. Some even argue that what we see as promethium lines might be misattributed features of more stable elements under unusual ionization states. Furthermore, conventional theorists are cautious to emphasize the dangers of overextrapolation. Just because a star seems unexplainable doesn't mean we should jump to the most exotic conclusions. Science, after all, progresses by explaining anomalies within the existing framework before invoking entirely new physics or extraterrestrial intelligence. The key, they argue, is better data, higher resolution spectra, longer observation periods, and improved models of atomic diffusion in strong magnetic environments. Yet even within the mainstream camp, there is growing discomfort. The star's chemical signature doesn't just push against the boundary of known theory, it repeatedly smashes through it. Multiple teams have independently confirmed the presence of short-lived isotopes. Its spectral composition is not just odd, it's unprecedented. And over decades of monitoring, no one has yet devised a model that successfully predicts or explains the full range of anomalies without introducing large, unevidenced assumptions. This discomfort opens the door to the fringe camp, a diverse group of thinkers ranging from alternative physicists to independent researchers and even SETI-affiliated scientists, who argue that HD 101065 may be more than just a natural object. One popular hypothesis in this camp is the artificial manipulation theory, the idea that the star is being altered by a technologically advanced civilization. They point to the star's inexplicable spectral lines, its apparent evolution, and its persistent, stable output of elements that should decay rapidly as evidence that some deliberate process is at work. Some suggest it could be a stellar-scale laboratory, a kind of nuclear forge, where exotic elements are synthesized for reasons beyond our understanding. Others take a more communication-oriented view, proposing that the star could be intentionally broadcasting its anomalies as a form of astroengineering signal, a cosmic calling card meant to attract the attention of any species smart enough to detect and wonder. One notable advocate for this view is Dr. Paul Davies, a theoretical physicist known for his work in SETI-related thought experiments. He argues that stars could, in theory, be used as information beacons by altering their elemental makeup or magnetic modulation in ways that carry a readable pattern. While Davies doesn't claim that HD 101065 is definitively such a beacon, he believes it's a candidate worth watching, simply because it defies all natural explanation to date. Other fringe theorists entertain even more radical ideas: that the star is alive, that it's a conscious entity, or that it represents a transition state between natural stellar physics and something fundamentally new, a process or intelligence that is simply beyond our comprehension. While these ideas are often dismissed by the mainstream as speculative or pseudoscientific, they continue to gain traction among those who believe science must remain open to the unimaginable, especially in the face of persistent observational mystery. There is also a middle camp emerging, one composed of more cautious but curious researchers who don't fully commit to either extreme. These scientists acknowledge the weaknesses in current models but stop short of invoking alien intelligence. They propose that unknown stellar processes, perhaps related to neutrino interactions, undiscovered particle physics, or exotic fusion pathways, could be responsible. This middle group argues for more funding, more telescope time, and more advanced simulation work to explore possibilities that fall just outside the edges of current theory, without leaping into science fiction. One particularly interesting perspective comes from Dr. Luciana Bianchi, an astrophysicist at Johns Hopkins University, who specializes in ultraviolet spectroscopy. She speculates that Przybylski Star may represent a temporary window into a rare stellar phase, one in which a series of magnetic and rotational coincidences align to create an ephemeral but bizarre chemical signature. According to her, we might be catching the star at just the right moment, before its spectrum returns to a more normal state. If so, this could explain why no other star like it has been found. We're simply lucky to be watching at the perfect time. Still, the fact remains that no single theory has successfully unified all the evidence. The star's weak hydrogen lines, the presence of short-lived elements, its magnetic peculiarities, and its apparent compositional changes over time simply don't line up under any conventional model. Each explanation, whether natural, artificial, or theoretical, solves only part of the puzzle while leaving other parts glaringly unresolved. And this is precisely why Przybylski Star has captivated so many. It sits at the crossroads of skepticism and wonder, science and speculation. It reminds us that even in a field as mature as astrophysics, there are still mysteries that defy explanation, still puzzles that demand new thinking, still stars that resist being categorized. What the experts say, in the end, is less important than what they agree on. That HD 101065 is not just another strange star. It is a cosmic enigma, one that could unlock entirely new realms of understanding, or shatter some of our most sacred scientific assumptions. In the vast, mostly silent cathedral of the cosmos, humanity has long searched for a whisper, any whisper, that we're not alone. Radio signals, fast radio bursts, distant exoplanets, technosignatures, strange galactic structures, each has sparked speculation, but none have delivered irrefutable evidence of extraterrestrial intelligence. We've pointed arrays at stars, launched golden records into the void, and constructed models for civilizations more advanced than our own. And yet, after decades of patient listening and hopeful scanning, the universe has answered us with nothing but mystery. That is, until Przybylski Star. What if, after all the misfires and false starts, we've been looking in the wrong direction, not at messages, but at machines? What if the most compelling evidence of alien intelligence isn't a signal or a transmission, but a thing, something engineered at a stellar scale? A silent, distant, yet unmistakably artificial anomaly that defies every law of astrophysics we hold dear? Could HD 101065 be exactly that? There's a growing argument, still whispered in halls of academia, still spoken with caveats and disclaimers, that Przybylski Star might be the first real evidence of extraterrestrial engineering. And this isn't just the rambling of UFO enthusiasts or speculative philosophers. It's a theory emerging at the uncomfortable junction between what we observe and what we can explain. Let's lay it bare. This star contains elements that do not exist in nature, at least not for long. Promethium, for instance, decays so quickly that even in the rare cases it's produced naturally, it disappears before we can find it. The half-lives of some suspected elements in this star's spectrum are measured in years, some in days or seconds. And yet they're there, again and again, decades after first discovery. If our spectroscopy is correct, this means these elements are either being replenished by some unknown mechanism or were synthesized recently, within the lifetime of modern observation. That alone is staggering. But there's more. The star's composition seems to be changing over time, subtly but perceptibly. It's as if some process, natural or not, is fine-tuning its chemical fingerprint. Its magnetic fields are not just strong, they're off-the-charts complex. Its hydrogen lines are suspiciously weak, and its spectral signature is unlike anything else we've found in the entire Milky Way. This is no mere statistical outlier. It's a violation of stellar theory. And if something breaks every rule of the game, we have to ask, is it still playing by the same rules? Enter the possibility that HD 101065 is not a star in the traditional sense, but a construct, or at least, something being used or modified by a civilization far beyond our own. It could be a Dyson forge, a stellar-scale factory designed to manufacture rare elements. It could be a broadcast mechanism, modulating its spectrum to encode information. It could be a monument, a display of cosmic power meant to be seen and puzzled over by any intelligent species lucky, or advanced, enough to notice it. In this light, the presence of short-lived radioactive elements becomes a kind of calling card. A signature not made of ink, but of technetium and promethium. A message not written in language, but in nuclear anomalies. A beacon not of light, but of impossibility. And isn't that ultimately the perfect message? Because if an advanced civilization truly wanted to announce itself to the universe, not to scare, but to intrigue, what better way than to create an object that should not exist? A star that violates physics is, in a sense, more powerful than any message we could decode. It doesn't require language. It doesn't require translation. It simply is. A cosmic riddle with no answer, only awe. Critics, of course, will point to more conservative explanations, radiative diffusion, measurement error, magnetic anomalies, or misidentified spectra. But none of those theories account for everything. None of them explain the consistency of the spectral oddities over 6 decades. None of them resolve the central problem. Why would so many unstable elements gather and remain on the surface of a stable, middle-aged star. At some point, when enough assumptions pile up to prop up a failing model, the simpler explanation is to step back and ask, what if our entire framework is wrong? If we abandon our preconceptions, that all stars are natural, that all stellar behavior must be explained through known physics, we're left with a chilling possibility that this star is not an accident, that it's not an anomaly, that it's a construction, or a project, or a signal, that it's meant to be seen. Even the SETI community, normally cautious and sober in its assessments, has taken notice. While no radio signals or modulations have been detected, HD 101065 is increasingly included in discussions of potential astroengineering signatures, a concept that's gaining legitimacy in scientific circles. The idea is that civilizations with sufficient technological prowess wouldn't send messages in bottles or flashlights across space. They'd reshape stars, build megastructures, or alter stellar chemistry as a kind of monument or communique. The term, stellar monument, might sound poetic, but to some astrophysicists, it's starting to sound plausible. And if that's true, then Przybylski Star might just be the Rosetta Stone of the cosmos, a deliberately incomprehensible object, designed to test the curiosity and intelligence of those who find it. So we ask again, could this be the best evidence yet? Not because it shouts, but because it refuses to make sense. Not because it follows patterns, but because it breaks them with surgical precision. Not because it's loud, but because it's impossible, and impossibility might just be the one thing we can all recognize as deliberate. It could be nothing. It could be nature laughing at us from 355 light-years away. Or it could be the first star we didn't discover, but found us. In the grand finale of our journey across time, space, and the boundaries of known science, we arrive at the question that has lingered beneath every observation, every theory, every lingering mystery surrounding HD 101065. What are we truly looking at? Is this a fluke of nature, an exquisite cosmic prank pulled off by the universe's unknowable mechanics? Or have we stumbled upon something far more profound, a message encoded not in language, not in mathematics, but in the very chemistry of a star? Przybylski Star refuses to be understood. It resists categorization. It pushes back against our models, our expectations, and even our imagination. It breaks the rules not with violence, but with precision, with care, with detail. It doesn't explode or flicker or fade in some overt sign of drama. Instead, it sits, quietly, stubbornly, showing us spectral lines that should not exist. Emitting the fingerprints of elements that vanish in moments elsewhere in the universe, yet persist here, glowing steadily in the stellar dark. It is, quite possibly, the most scientifically infuriating object we've found in the sky. And that frustration may be exactly what makes it so important. Because the deeper we go, the less it makes sense, and that is where wonder lives. If this is a natural phenomenon, then it is nature at its most cryptic, its most experimental. Perhaps we are merely looking at a rare but entirely physical process, one that occurs when magnetic fields, atomic diffusion, and stellar geometry intersect in just the right way. Maybe, one day, a new generation of physicists will crack the code and reveal how elements like Promethium can be produced or preserved without intelligent interference. Maybe this is just the extreme edge of stellar behavior, unseen, misunderstood, but ultimately still part of the cosmic rulebook. But even that explanation would be extraordinary. It would rewrite what we know about fusion, element decay, and stellar chemistry. It would demand new physics, and that, too, is revolutionary. Yet if it isn't natural, if the sheer weight of contradiction becomes too much, then what we're looking at may be the first clue. A clue that someone else has been here before us. A clue that intelligence may not announce itself in bursts of radio or directed beams of light, but in artifacts of function, a forged star, a crafted anomaly, a gravitational monument built in the sky not to communicate with us directly, but to challenge us. To see if we notice. To see if we ask? After all, what better way to test for intelligence than to leave behind something that only intelligence could notice is wrong? If this is a message, it is not one of greeting or warning, but of provocation. It asks, can you see the impossible? Will you look deeper? Will you challenge your assumptions, question your models, discard what's familiar to grasp what is true? And if we can, then perhaps we've passed the first test. Or maybe we're still in the dark. Maybe HD 101065 is just a ghost in the machine, a product of randomness, a beautiful misfire, a reminder that the universe doesn't owe us answers. Maybe it's just a glitch, and we're the ones reading too much into a shimmer of spectral static. The universe, after all, is vast. Even anomalies are bound to happen when you're watching billions of stars. Perhaps this one is just the cosmic equivalent of a typo, a rounding error in creation's equation. But if so, it is a stunningly elegant typo. One that endures, that evolves, that changes its story as we change the instruments we use to study it. And that alone is enough to make it worth our attention, our wonder, our reverence. So we end not with answers, but with a feeling that beneath its faint light, HD 101065 may be something far more powerful than a mystery. It may be an invitation. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.